Ah. Camera is here.
As in on the screen, drag the camera. You have to disconnect your audio. So here's
Okay, great. All right, shall we resume? Okay, all right. So, concurrency, it's a problem because it leads to complexity and difficulty. So, I mean, I don't want to give you examples of, I don't want to, a lot of these talks start with giving you examples of, oh, this bug in Cassandra and that bug in blah, 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 and, complicated things and lots of stories and so on. I don't want to give you all that, right? We all know this. This is just a very general problem. The problem is that of interactions. If you have multiple non-local pieces of code interacting with each other, that is going to create a comprehension challenge. When there is comprehension challenge, you're going to make mistakes. And when you leave mistakes in the code, it's going to lead to operational issues. And then your pagers and beepers will go on and your life becomes hell at that point. And then, the consequences are, I was talking about operational challenges, and then there are expensive bugs. If your major service goes down, it could, the damage could be hundreds of thousands to millions of dollars. Okay, so we had this Civl Verifier that we're going to talk to you about today, right? So, all static verifiers, it's a static verification, right? Meaning that there's a program text, it has to be consumed by a tool chain that looks like a compiler, right? And it's going to give you error messages, which you can fix. And at some point you get a certificate that, okay, whatever specification you were trying to prove is satisfied. So all tools, verification tools of this ilk, they have standard goals of verification: scalability, precision, and automation. It's hard to achieve all of them together, right? So we have, those kinds of goals also, but, our particular compromise or trade-off that Civl is shooting for. Sorry, what?
You have to touch.
I have to touch? Oh, I have to keep touching the laptop. Okay. I see.
Same problem with the other. We couldn't solve it. Sorry, that's the set.
Okay, but I can keep touching it, no problem.
Yeah. I don't think it's related to you touch it. It's related to tables.
Oh, I was standing on. Okay. All right. So what is Civl trying to achieve? It wants to achieve scalability and precision for a large class of concurrent systems, but it's going to compromise on automation. Because, the people who work on Civl, their background is automation, in general, automation at any cost whatsoever, right? So if these people say that we can sacrifice automation, you can just trust them that they will not sacrifice it too much. You see what I mean? So that's the idea here. So, yes. Yes.
You're saying standard goals for verification or scalability. I cannot see that many people actually are trying to even talking about their scalability as a verification target. How would you define that?
What does that scalability mean?
No,
for me? No, I mean, I can explain to you what scalability means, the verification context. Very simple, right? When you have a Java program, right? You run the compiler on it. Is the compiler going to bar fetch you if the program becomes too big? Like 1,000 lines, 10,000 lines. Looks in compiler.
It's the size of the program, not the execution.
Yes.
I know.
Yes.
Never mind.
So the thing is that verification tools tend to fall off a cliff very quickly, scalability cliff, and we don't want that. We don't want that. We really don't want that. I mean, I think that oftentimes people who work on verification pay lip service to it. But I can tell you right now, I'm not paying lip service to it. This is the goal, scalability, because we will sacrifice automation if we can get scalability. Okay. All right. So this is the outline of the tutorial. There is something, Civil is not your, standard verification tool chain, right? It has some machinery in there that is not so well known or not so commonly used. So we're going to spend some time using a simple example to explain that machinery. And that machinery is going to be the ticket protocol. Okay. So we'll talk about the protocol and then how to write it and how to prove it and so on. And then maybe that will take us all the way to the break because we're going to take it slow and there could be lots of questions and it'll be interactive and discussions and whatnot. Then after the break, I'll talk about some more sophisticated advanced topics, such as those things. I'm not going to talk about them right now, but there'll be more advanced topics, more advanced uses of Civil, which are necessary in order to be able to build larger systems. And then I'll talk about two more, realistic larger systems that have been developed with Civil. And with this, I will hand it off to Constantin to start the first part of the talk.
Okay, thank you. So I hope this thing will not bother us too much. Okay, anyway, so basically I will sort of start with this example to show sort of the main, it's like a sort of introduction into Civil and what are the main components. So Civil is about proving programs. So now what do we mean by programs? Basically, these are like concurrent programs where we have some number of shared variables. Programs use procedures. I mean, we have no restriction on sort of the control flow. And then one can use, I mean, inside the program, we can have the usual assignments, conditionals, whatever loops. Then procedure calls can be either synchronous, so meaning like in a sequential program. Yeah, I don't know.
You want to try to stand on that side here?
On which?
And
On that side.
But I don't think he's touching the cables at all.
No.
Yeah, maybe just the bumps.
That means
Yes.
okay.
I think someone, so maybe someone's gonna.
No.
Yeah, okay.
Okay, but maybe you move from there. No.
Yeah, okay, we'll try that.
And if you go back to the presentation, use. Huh? Yeah, very well. Okay. We'll try to stay here to see what happens. Yeah, so I was saying, so procedure calls can be synchronous, like in a sequential program. Then you can have asynchronous calls, which sort of it's like spawning a new thread that will execute that procedure. Or you can have parallel calls where essentially it's like a fork join model, so you can call multiple procedures and then wait until they will finish and continue. Then types, I mean, it's the usual stuff, you have Boolean data types, arrays, whatever. Basically, this is based on Woogie, if some of you know about it. So this was like an intermediate verification language. So basically, whatever data types you can define in Woogie, you can also define in Civil. And basically, as sort of in order to represent computation, so basically you have procedures. So a program is a set of procedures. You can have a main procedure if you want to define an entry point. And basically every step of computation is, I mean, steps of computation are, at least when they verify, when they modify shared variables, they are these gated atom captures. So you can think of this as, so basically they are like a pair formed of a gate, which is like a condition and a step, so transition relation. And then if that condition fails, this means that the whole program fails. And otherwise, if that condition holds, then you will advance according to the transition relation. Right? Anyway, you'll see more or less, I mean, through the examples. And basically with all this, you can model whatever you want in terms of shared memory concurrency or message passing. Basically, we hear when we talk about message passing is as usual, you code channels as shared variables, like shared arrays and so on, and then send and receives are like modifying these arrays. And then, yes.
Yeah, I think about this is, I have an algorithm and I can write the algorithm in Civil and then verify it instead of verifying the implementation.
And you can do both in some sense.
No, but the thing is, it cannot consume a C++ code. Is that what you're asking? No, it cannot.
Yeah. It's like sort of code similar to Owicki, I mean, extended with these features for concurrency. Okay. Yes.
So is the code being executed?
No, it's not executable. I mean, I think there were some works even on the level of Owicki extracting executable code, but
So maybe the question is there a code generator? Can you run the code that has been written?
Yeah.
We don't have a code generator. Right?
and then as this is all this is to represent computation, and then if you want to specify the behavior of your program, you can use as usual contracts and procedures, pre-close conditions, assertions. For concurrency, we'll have something specific that I will present later. Okay. Okay, so basically now if we talk about, so this is like sort of the overall picture of what the program is. Now, when you are trying to prove a program being correct, essentially it's like a sort of combination of tactics or like variations of existing tactics, but they are combined in a certain way. So let's say at the more core level, when you reason about concurrency, we are using sort of a compositional variant of Owicki-Gries. For those that know, otherwise I will just briefly explain what Owicki-Gries means. So basically you are doing proofs for each like sort of thread, and then you want to show that the proofs that you have for each thread don't interfere for some notion of non-interference. So basically this is at the core level of how to reason about concurrency. Then sort of this core reasoning is extended with several proof tactics. So there is refinement. So basically whenever you want to prove some complicated program, it's very natural to try to simplify it and then maybe in several steps. So it's not like a single step of refinement, you can do it in many steps of refinement or abstraction, depends on which direction you are. Then there is the reduction where, I mean, it's very common in concurrency that you have steps that commute between themselves. So then if they commute enough, then you can simplify sort of the class of interleavings that you need to prove correct. So this is the reduction. And then also very common in concurrency, I mean, you need a way to sort of, when you reason at least about the interference between different threads and so on, you need sometimes a way to know that some action is of a different thread and not the same thread as you are looking at. So then you would need a way to sort of distinguish, to talk about, specify something about the control flow. And we are going to do this using the linear type system. All this, basically, this is just a high level view. I will show this on an example. Okay. So basically, this is the example. So it's a sort of protocol if you want an algorithm to achieve mutual exclusion. Okay? So basically, you have a number of threads. Here, each thread executes this procedure that I call customer, and what you want. And basically, they do some stuff, and at some point, they enter some code that it's supposed to represent the critical section. So basically, what you want to ensure is that there are no two threads that reach this point at the same time. This is the standard mutual exclusion.
SNT are shared and M is local.
Yes, now I will explain the product. Okay, so basically you have think of it is like a standard model of a ticket. When you go to some office desk and so on, you go there to some machine, take a ticket, and then when you see the number of your ticket, print it on some screen, then you put it to the desk. Okay? This is modeling exactly the same thing. Using two shared variables, T represents this ticket machine where you get your tickets, and S basically represents what is printed on the screen. Okay? And then whenever you, as a first step, you first acquire a ticket, meaning you read the value of this shared variable, and then this gets incremented. So the next guy will get a different ticket. And then when this ticket that you have equals this value that is printed on the screen, so meaning that sort of you are allowed to sort of use the service in some sense, then you enter the critical section. Okay? And of course, when you get out, this value that is printed on the screen is represented by this counter S gets incremented. Okay, so that somebody else can get treated. Okay. So basically, I had some picture here that basically this is it. So you can have, for instance, if we talk about two guys, then they go to the ticket machine, they get some tickets, and then there is some desk there that sort of for at the beginning prints value 1. So this means that this first guy can go. Then once this guy is handled, the value increases. So then this other guy can go. So, okay. So basically, this is it. Okay. And now we want to sort of prove this protocol correct. But before that, we need to specify. So we need to specify mutual exclusion in some sense. So here we do it in a particular way by introducing a sort of an auxiliary variable. So basically we assume that each procedure, so basically we have access to the thread ID. Okay, so in some sense, each procedure is parameterized by a thread ID. And then here, whenever we enter the critical section atomically at the same time, we update this variable, which is also shared, called CS. Okay, So a convention that I will use all the time is that whatever I write on a single line, it's executed atomically. So these two things are executed in something else. Okay? And then when I sort of want to get out of the critical section, I have an asset that checks that I'm really the one that gets out of there. Okay, so in some sense, imagine if mutual exclusion wouldn't have been satisfied. So some guy will set the CS to some value, then some other guy will set it to a different value, and then this asset will fail. Okay, so basically, this is a way of modeling mutual exclusion. Okay. And of course, when I get out, I set this CS value. Okay. Okay, so basically, this is a way to specify it. Now, let's say we want to prove basically that in some sense this asset never fails. Yes.
You should brush the wine on the same wine arrows.
Mm-hmm.
Does it make any difference here? Like if we split assume and send CS. The last time
I mean here it
swap CS and say increment, and in that case it should not break because essentially you only terminate section in the increment this.
Yeah.
But you could more experiences like.
So I think that you are right.
Yeah.
That you're saying that if you took this line and you put it on the next line, so there are more possible behavior, would that affect the correctness? I think you're right, it won't affect the correctness. But why make life more difficult? It's a ghost layer that you're adding, right? Then you can always make it atomic with the other things, right? It does not affect the correctness, you see. Yes.
So you are saying that a complete line is executed atomically, not a statement, a line.
Yes, a lot. Yes.
Mm-hmm.
So basically, this is in a single step of computation. I do both things or all the three things.
So CS is the ghost shared variable and TID is the ghost local.
Correct.
Which one is a ghost local?
PID.
TID, yes, yeah. Okay. Okay, so basically, yes.
So
Hmm.
why did you pick this as a correctness property? Why does this translate correctness to you? I mean, usually the correctness property is mutual exclusion.
Yes. So now I explained before, no? So if assumed mutual exclusion is not satisfied, okay? So then it means that basically there would be one guy that sets this to PID, okay? So basically two guys to be at the same time in critical section, okay? It means that there are two guys that execute this line before going to this last line. You agree?
I don't think that's what he's asking. He's asking, why did you pick this style of specifying mutual exclusion? How would you do it?
I would set a flag, critical is taken, and
Yeah.
and then assert that when I am in the critical section, then the critical section is free.
So you use a Boolean
Yeah.
flag as opposed to a thread ID value flag, huh?
But then how do you distinguish whether it's yours?
But the thing is that I think Andreas is right, that the critical section property can still be expressed that way.
Hmm.
So here, what's happening is that we are doing it, we are putting a little bit more information there. So I agree with you, that's another way of doing it. But let me ask you this. Do you agree that this also captures critical it has more information than your method, but it has adequate information too? Do you agree?
Yeah. It's something with your method, if you use the weaker specification of correctness, I mean, it would be natural to say the number of processes that is in the critical section is smaller equal to.
No, so I know what you're asking, and no, the method does not depend. What you would do is you would start with your specification, and then what I would do is I will again introduce another ghost variable CS, because it is very critical for my verification method, and it will be used to verify the original assertion. So this is just a little shortcut, but there's nothing fundamental about it. I'll continue to do it even if we start with your specification.
Yes.
Isn't that proposed specification, of the gentleman in the first row, exactly the first statement and the last line, which is a Boolean, CS equals to TID, and CS is actually what he's proposing, which is a shared variable. Doesn't that boil down to the same thing?
I did not even understand.
He's proposing, so what he was proposing was to have another shared variable. It needs to be shared because
Yes.
the other threads need to be understanding whether somebody occupies the critical section or not, right? So that's a Boolean he was proposing. And all I'm saying is, well, that Boolean is there, it's just hidden in the quality check on the last line of CS equals TID.
You're absolutely
saying again, because CS is actually a shared variable.
Yes, that's correct.
This is a refinement.
Yeah.
Yeah. So then you can say that.
Okay, sounds good. So basically, this is sort of what this is what we are trying to prove. And now basically before showing how we are going to do that with Civl, I will show, let's say, a more standard or classic proof using the standard, let's say, or in some sense, original Owicki-Gries or some thread module extension. Okay. So basically Owicki-Gries, as we were saying, you have like a 4-style proof for each thread. Okay, so basically this will be using the usual 4 triples. It's just that you want to show that proofs of different threads do not interfere. Okay? So basically you want to show that the assertions you are using in the proof of one thread are preserved by any action of a different thread. Okay? So basically you take an assertion P in a proof of a thread I, and then you take a step of another thread J, and then you want to show that sort of this step preserves the P. Okay, and of course you are allowed to use the precondition of A.
This O triple is for thread I.
Hmm?
The one that O triple that you put here
Yes.
is for the A here is for thread, which thread?
So the A is, so here I'm just give something more intuitive. I'm just distinguishing between P being in the proof of a thread I and A being in the proof a step of a different thread J. Okay. But actually in the proofs, I mean, you are not going to use that, or it depends on how you implement that.
So I guess the question is, the P, you can use local variables of thread I.
Yeah.
Yes.
Yeah.
Yes.
What is pre A?
So the precondition of A, so basically the A itself is a step in the, but you have it's in a step in this thread J, but for this thread J, you also have a proof. So you have a for triple associated to A.
So, okay, so every event is associated with some triple.
Yeah, because basically we need a proof for every thread. So in every thread, you will have a for triples for every step. And this precondition is really the pre of that for triple. Okay, so basically this is what we are going to do first, to give a Owicki-Gries proof for this protocol. And basically, as you may know already, this proof methodology is not complete, I mean, as it is. So in general, if you want to prove any kind of program you want to imagine, you have to introduce auxiliary variables. So these are like those variables that are we introduce just for the purpose of the proof. And here, so basically the ghost, the auxiliary variable that I'm going to introduce is a function that maps thread IDs to integers, which are basically represent the tickets. So basically this ghost variable is updated every time a thread gets a ticket, and it's updated by saying that now the TID that acquired that ticket is mapped to the variable. And now once I have this auxiliary variable, now I can state the number of assertions, okay, that eventually will give me a proof. So for instance, something that I can say now, for instance, is that the image of this function at the beginning and actually at all time in this during this execution of the protocol, it's actually the interval from 0 to t open on t.
T is TID.
No, t is this variable, the t here. Okay. So basically, at every point, so this is like a sort of invariant, that invariant. Okay. At every point, the set of tickets that are acquired are exactly this interval from 0 to the current value of this t. Okay.
Will you declare the F? I'm just wondering what the type of F is, what's the variable?
So I didn't declare it, but f is a function from thread IDs to integers.
It's a map. It's a literal map.
And thread IDs, do you assume they are natural numbers or
Yeah.
when
Yeah.
you don't need to?
Yeah.
But it's an infinite set.
Yes. Okay. And also something that I can also say all the time is that basically any two threads acquire different tickets. Okay, so the value of f for every two different values is this ticket. Okay? This is also like an inductive invariant that gets preserved.
This pre and that post is not the critical section of code.
Which one? The pre?
You started out with checking the critical section.
Mhm.
How is this?
Yeah, for the moment, this is not yet enough. Okay, and just so these are some statements that I can make already, but we need to enforce them. Okay? And also something that also holds all the time is that S is less than equal to T. Okay? So basically, these are like some statements that you can. And but of course, for now, for instance, we cannot prove that these are set holds. Okay, because for instance, here I don't say anything about CS. So it means that I need to strengthen this. Yes.
So when did you first establish this severe? It's not the establishing function, right? Because it should hold the overall state.
What do you mean?
No,
You're talking about this invariant, right?
no, so everything in green.
So this customer here has a precondition which is not shown. You can just think that because this assertion in green is before the first statement in customer, you can think that this is the precondition of customer. So what you are, there's an assumption here that when you launch customers at the very beginning, this holds.
Yeah.
Right. And after that, everything's changed.
Okay. Okay, so basically, sorry to this.
So why does this initially hold?
Because initially F is empty, no?
And S is equal to, so initially, F is empty,
S and T are both
F
one.
and T are both one.
And yeah, and basically there is no, it's a 0, 1 is, I mean, this interval will be empty when T is equal, so.
And this is my conclusion. So I still don't know what the type of F is.
Okay, well,
F
can you
is
write it? Can I type something?
Yeah.
There is an uninterpreted type called int. And there is a type called int. And the type of F is a map from int to int. Map as in the SMP map. Okay?
Int is not identified.
Int is interpreted. But int is an uninterpreted set.
Okay. Next.
Yeah, and I'm still, I mean, this is F, the image is the interval from 0 to T. So initially the image of F goes from 0 to what? To -1.
No,
It's empty, right?
It's empty.
Zero, if the
By convention, the interval 0, 1 open is.
yeah, empty set.
It's an absolute zero.
It doesn't contain the 0? Doesn't contain the 0?
Ah, it contains the 0.
You can change this to one.
It's
One.
okay. So
Oh,
0, yeah, it's 0 open.
So by the way, I made a mistake. It should be a partial map from TID.
Yeah, it's a partial.
It's not a total map. It's a partial map from TID to
Yeah.
int. That's one way of thinking about it, or you can think of it as the total map from TID to option of TID. That's another way to think about it.
Yeah, and here it's open 0. Yeah. Okay. Okay. So now we have to add something. So actually, we have to add some things to this assertion, not only because this assertion doesn't pass, also because sort of we don't satisfy non-interference. Okay. So, I mean, let me give you some, also this allow me to show what we mean by non-interference. So if I take this assertion that I wrote here, okay, and I do a step, we have some thread, actually we don't care which thread, then you see that in this case, this assertion remains true, okay? Because if my image is from 0 again open to T, and I take the current value of T, okay, means that I still, this assertion now is holds because the T now also it gets incremented, okay? And I also get that the values of F are distinct also because before all values were in this interval and now I'm taking the next value and so on. Okay? So basically this LDS remains with.
And so now you have to argue this for every state.
Yeah, now you have to argue for every state. And for instance, if we argue for, I have this assertion and I take the last step, okay? Since I don't say anything about CS, so it may be possible that this assertion goes through, okay? And then what I get, I increment S, okay? And for instance, if here S equals T, then by incrementing S, it will not be any more smaller than or equal than T. Okay? So this means that this is not yet resolved. Okay? So now I have to add more things, and we can add the things in blue here. Okay, so here, for instance, I can say that the value associated to TID is M, and then I can say here that actually S is strictly smaller than t, okay? And then the similar things and so on. And now you can believe me that sort of this proof will pass, okay? All big things will satisfy the fields, okay? And this was an example, okay? And I can also, now we can also show that the assertion holds just because we have this equality in that assertion. Now the assertion can be discharged. Okay, but anyway, basically this is, I mean, just to give you a flavor of how we do this using standard, let's say, Owicki-Gries. But sort of what we, I mean, the focus of this tutorial is, of course, to show how we do this in Civl. And basically in Civl, we will do this, I mean, using several, at least 1 or 2 steps of abstraction. So basically we'll take the original ticket protocol and we'll try to abstract it to relax the behaviors. Okay? And we will do actually a sequence of abstraction steps, not just one. And also what we will introduce on the way is sort of this compositional variant of Owicki-Gries. So sort of build on this methodology that we saw before. It's just that in some sense it's compositional, and I mentioned in what sense. And then also we will use commutativity reasoning. You saw that basically also an important thing is that you see here all these assertions are sort of global. They talk about everything. I mean, all these assertions, they talk basically about all variables at the same time. Okay? So the one good thing that we will see in the Civl proof is that sort of we'll try to sort of separate concerns in some. Okay?
So,
Yes.
Can you go back? So you said the assertions here, like it's in the first assertion, everything is global, right? F is global, S and T are global.
Yes. Mhm.
So you're saying you want to get rid of that?
No, I'm just saying that here these assertions talk about all variables, if you see.
All variables meaning
All the shared variables, if you want.
S and T
Okay.
and F.
So in some sense, I'm reasoning about everything at the same time. Okay, I want to separate concerns, for instance, talk just for a moment just about the T or whatever, I don't know, and in a second step, look at other variables and so on. But maybe if that is confusing, let me advance and then it will be maybe clearer. Okay. So as we said, we will do a sequence of abstractions. Okay. As we saw already in the Owicki-Gries proof, we need auxiliary variables. I mean, this is a sort of thing that sort of it remains, because even here we are using the sort of variant of Owicki-Gries, so auxiliary variables will still be needed. Okay. And basically in Civl, introducing ghost code is seen as an abstraction. Okay. So basically we have our original code, okay? And we'll say that this original code is a refinement of code where I added some ghost code. And here what we add is a ghost code, so we add an auxiliary variable, which is now, we don't need it anymore to be a function, it will be a set. And it will store all tickets that are acquired, okay, during the execution of the protocol. And also we'll have this variable CS that we will still add it and use it to specify basically material exclusion. Yes?
So first question is,
Hmm.
this is an abstraction, the blue thing is an abstraction of the final thing or?
Yeah, I mean, it's an abstraction in the sense that, I mean, basically here, I mean, it's an abstraction that, okay, maybe it's improper, but basically what we want to say is that all, okay, I will tell you in which sense it's an abstraction. All behaviors here, okay, are included in this, are included in the behaviors of this one. Okay?
There are more.
Yeah. I mean, it can be even equality in some sense. Okay?
So it's more, at this point, we are setting up for abstraction. Abstraction has not really happened. All that has happened is that there's a conservative extension of every execution on the left side with an execution on the right side. We have augmented each execution with some extra state.
But I mean, why
But-
it is
But
really
For
important.
this example, I
Yeah.
understand, but in general, this step, this first step, what can you do? in this step? What do you do?
So in this, so this step by itself, what you can do is you can prove some invariants about the augmented program.
Typically, these invariants are saying that it's every execution has a like simulation here. There is a one-to-one
So-
performance of some sort, so
No. Imagine, it's not true in this program. But let's say that just by virtue of adding a key, I expand the vocabulary in my program enough that I'm able to write an invariant that is able to discharge this assertion. Right? Then I will just do that and I'm done with my proof, right?
you would actually do that. In the last slide, you have in your invariants, you have most of the
Yeah.
basically.
That's right. So that was the classic Owicki-Gries. So yes, that's what classic Owicki-Gries is, which is that you add stuff and then you get the capability to write an invariant and then you just done the proof. It's a one-shot thing. But starting from now, you're seeing this more involved approach. And it will be more involved for sure. But you have to just trust us that there's a pot of gold at the end. You have to just delay it a little bit. Yes.
How do you ensure going along these steps when you add more things that it actually remains a conservative extension of the motion methodology?
Oh, that is, you have just summed up the entirety of Civil. All the machinery is just for doing that.
There is a proof system underneath. I mean, there are like sort of this proving that this abstraction is sound. It's sort of compiled into a set of verification conditions that are given to an SMD software.
So more or less automated this.
After, so yeah, so you can specify the abstraction, but checking that it's a conservative extension, you're not losing behavior, that part of it. Yes.
Okay. And you see that here, even if it seems like not a proper abstraction because we are not adding behaviors in a very proper sense, I mean, it still makes sense that every time you introduce those code to check that it doesn't restrict some of the behaviors of the original program. Okay? That this close code is released, this addition is some. Okay? So in some sense, in Civil, you can sort of check that. Okay, so now we arrived at this point. So now we can already state some invariant, okay, about this. So if you look on the left, so basically when we did this, so we added this variable t and so on, we can already say that sort of the set of required tickets are in this interval up to t. Okay.
So there is some confusion here with this minus infinity and so on, right? There's various versions of ignore that.
Yeah.
Let's just assume that the left side of the interval is something that is consistent with what Constantin had said before.
Okay.
Okay.
But
There's
I just want to say that sort of you acquire all possible tickets that could have been acquired up to and excluding t.
Yes.
Okay.
That's right. Yes.
It was. And you see now we can already establish this invariant. Okay? That sort of this assertion holds all the time. Right? And actually you can also, so here it's a classical Owicki-Gries. So basically you can also show that sort of this satisfies non-interference. Okay. So basically every other, if I have this, if this holds in some thread, the action of every other thread will still preserve this property. Okay. Now basically this is how we would write thing in classical Owicki-Gries. Now basically in Civil, you have another way of writing that. And these are for the purposes of also effectiveness of writing proofs, but also for obtaining some more compositionality. So basically, we are going to declare what we call an yield invariant. Okay. So basically, this assertion that we wrote here in Civil is declared as an yield invariant, which is, you can think of it as a function that sort of is a sort of check some Boolean condition, right? I mean, in general, it can have parameters. I will have an example later that where it has a parameter. And basically, afterwards, you can call it at all sites where you want to state that data session holds. Okay. So you see that in terms of the ergonomy of the proof, in some sense, this is much simpler. But also, one crucial thing is that when you check non-interference, you don't have to parse or like look into the proof of a thread. You just look at the yield invariants that are declared, that are sort of taken out of the proof of the sequential proof of a thread. And you look at the yield invariants that are declared, and basically you prove that all these yield invariants satisfy non-interference. Okay, so basically they are preserved by every other thread. Okay? So you can think of it as going towards relay guarantee, okay, in the sense that sort of this program is correct as long as all these yield invariants by any other thread that you can have in the system are preserved.
So you said something about the record. That's not clear to me.
What I mean, sorry?
The ease of this kind of proof.
Ease in terms of ergonomics.
I mean, in the sense that you can sort of already reuse, I mean, you write the invariant, I mean, even in terms of numbers of letters, okay? I mean, I just write this invariant once and then I keep reusing it whenever I need it.
So why is it not ergonomic, right? I didn't have to repeat this fact t is equal to minus infinity t everywhere, right? I just had to write call yield everywhere. Imagine now that this invariant took 100 lines. So you write, if there was 10 lines here, you would have to write it 1,000 times, right? But in this time, you would have to write it 100 plus 10, 110 lines. Right?
Okay.
So it's not related to the fact that the precondition is always the same. This is how I understood it, right? Before you had for each action, you had a different precondition. Now it's the same.
No, but that's not true.
We are in an intermediate step here, and we didn't arrive to the proof of it.
No, but let me ask you, supposing that this one, these two are same, and this one was different. All that would happen is that instead of a single yield invariant, we would have two.
And we will have that.
And we will then say call yield one here, here you will call yield two. So if there is commonality, you get to exploit it. If there is no commonality, no problem.
Functions like the parameter.
Yeah.
Yes, yes.
And so, okay, now you're calling them function calls.
They're not really, they're more like procedure calls. Yeah, but
So now, do you also want to define this new augmented program? Does it matter?
so these you can, this is much easier because these are just annotations. These calls here,
No.
you can basically think of them as annotations. They're erased. Yeah, the erasure here is so simple that you don't have to think about it. Yeah.
I mean, this sort of keywords, yield invariant and so on are fundamental. So I mean, it's not. And in that sense, I mean, when you see these keywords, you can understand that these calls are equations, etc.
So here, okay, that kind of stuff. Now here the proof obligation was that, every pair of repost is okay and also not. What is the proof obligation here?
Okay.
So here you have to basically whenever these are like standard obstacles, okay. And now also you have to prove that these yield invariants, they satisfy non-interference as it was defined before, meaning that this statement is preserved by any step in my program.
So you're saying that bit is now because of reuse reduced.
That is also reduced. Yes. Because imagine, consider the case where these three are all the same. If any standard implementation of Owicki-Gries, the old Owicki-Gries, would do 3 times 3 checks. But this dude over here is going to do 3 times 1 checks. So the complexity goes from number of lines of code, quadratic number of lines of code, to number of lines of code times number of yield layers.
Okay, so basically this is where we are. So this is one step of abstraction and sort of what yielding value or what invariants or what statements we could establish about this first step. Okay. Now we will go together and we'll go we'll advance define a new abstraction step. Okay. And now this is basically really an abstraction. Okay. Where basically what we will do, instead of saying, okay, you get the next available ticket, okay, you are saying just take any ticket as long as it was not taken before. Since I have this auxiliary variable that keeps all the tickets that have been acquired before, this I can just express by just saying, okay, get an arbitrary m and assume that it doesn't belong to this 17. Okay. So yes.
How would I come up with this?
Okay. This is like coming up also with the invariants.
Okay. So it's like part of the process.
Yes. Okay. Yeah, we are still in the real mode.
So actually, the reason he's asking this question is because you just pull this kind of like out of thin air, right? Because you haven't shown what you do after this. Why this particular abstraction and not some other crazy thing?
Okay. You'll see the reason why we put that in. Okay. And basically, you see now that in some sense, what we did with this abstraction, we just proved that sort of these tickets are acquired in a way that no two threads acquire get the same ticket. So for the moment, I just proved that. Here you see it could have been instead of T++, it could have been at T+2 or whatever. Okay, the abstraction would be the same. Okay. So this is one point of, in some sense, separating concerns. Okay.
So with how the semantics change. So if
yeah, here I have more behaviors now. Because here I would have acquired the next ticket here, which would have been 2. Here I can acquire 10 directly immediately after.
And so now from the blue thing to the yellow thing, what is it that you want to relate? How do you want to relate the blue thing? And
so now what I want is that the behaviors of the blue are included in the behavior of the yellow. Yeah. Yes.
Is this something that has happened automatically, or is this something that you have done as a user?
You invent the yellow as a user, so this you have to write yourself. But now this check again, this is done. Yes.
So we now became non-deterministic, right? So it also can happen that somewhere later we became less than we have been before.
Yes.
So in that sense, if we keep increasing S, then it will never go back to the value smaller. So every
you sort of here we did just reason about safety. This program can block more often than the original subset, but we don't care about that. We just care about correct safety.
Beautiful. Yes, wonderful. Yes. This program can deadlock. That's okay. All you were interested in was proving the assertion. That's okay.
So you see, it's important that the yellow includes everything, does at least everything that was possible in the blue. But if I have more things, now it's just the job of proving that these more things still satisfy the spec. And if some of them deadlock, anyway, I don't care.
okay.
No, ask a question.
Yeah, no, I think I might get lost what we're going to do with the yellow problem.
Okay, so yeah, so let's go. Let's keep going.
Okay. Now, basically, the reason for introducing the yellow is to sort of introduce, prove that, for instance, these two things, these two lines, can be assumed to execute as one step. Basically, remove the interference point in between these two first lines. So assume that this is done one atomic section. So let's see how we can do that. So basically now here it's another ingredient in Civl, which is related to commutativity reasoning. And it's also, it's a sort of an extension of builds on the, if you have heard on Lipton's reduction theory. So basically, in some sense, you talk about statements that commute, okay? Now you can commute in two directions. Either you commute to the right of some other step or to the left. So then you will have right or left inverse, okay? Now, basically what we can show is that sort of this statement that we have done here, and now you see the purpose of why we define it this way, it's actually a right mover. So what do we mean by that? It means that if I execute this statement, okay, and then I have some other step of some other thread, okay, then I can reach exactly the same state as executing this other thread first, followed by this statement. And you see that there are trivial things. I mean, if I execute this statement and some other thread does this, for instance, it's clear that I reach the same state because the sort of the two steps relate or access different variables. Okay. So in the end of the day, the important case is what happens when I have one thread that does this and another thread that does exactly the same. Okay. And basically, this is the situation here. If I have one thread that chooses some m, okay, so this is my thing that I want to show that it commutes to the right. Okay, and another thread that does the same statement. So basically, it will choose a different ticket n prime. Okay, so I want to show that I can reorder these two and reach the same state. Okay, the same valuation for every same configuration. Okay? And actually, this happens because you see, if I choose M here and then I choose a different, when I execute this other thread does something, it will choose a different M prime that was not already taken. Okay, so this means that it can still take this M prime because it's still not taken, even if it does it before. And this guy can still choose M because here it was already, I mean, we already had the fact that M prime is different from M, and it will remain true even if I reload it.
Why are you not talking about blocking? Those partial executions that would have blocked because you chose the same M.
I mean, if we block, we don't violate any safety, no? I mean,
So in that case also you can argue about right.
So you don't have to argue if one thread did something and after that another thread is not able to do something, is the execution is not a problem. So I don't have to argue what commutativity in that case. By the way, there's something very critical that happened on the last slide that I think you forgot to highlight, Constantin, which is that little t that was here. It disappeared as you went to the right side in the yellow box. So it was hidden. This is very crucial because otherwise that little t was the obstruction to doing commutativity on the blue program. Right?
So instead of the S++, you can also do Havok S.
yeah, I can do some substitutions. I mean, no, you cannot do that because then since these tickets now are taken in arbitrary orders, if you start also making the S in arbitrary, I mean, moving back and forth, and
If you introduce more networks with the safety issues,
yeah, but
No, I think you will not be able to prove. I think what you're saying is that if you have a S here, you should still be able to prove this assertion on the abstraction. I don't think that's true. I think you lack too much detail.
Really?
Yeah, I think so. I'll have to think of the.
no, I mean, he may be right because now basically with this abstraction, you can prove that sort of just one thread, I mean, just one thread can acquire a ticket before entering the section.
So I don't know.
No. Yeah.
We can see whether the
Yeah.
proof goes through, right? When you didn't have.
Yeah.
So we can keep going and then we will see whether the proof goes through with that abstraction also. So keep going.
Okay.
Any questions about the commutativity business?
So why is it not both mover?
I mean, if it's probably a both, if you, I mean, anyway, it's probably a both, but it's just that in this case, we just require it to be a right mover. Okay, so now why it's important that it's right mover? So now, you know, now we can use Lipton's reduction theory, which says that if I have a sequence of statements where I start with the sequence of steps that are right movers, then some arbitrary step alpha, and then a sequence of steps that are left movers, then I can assume, it's sound to assume that all this executes in a single indivisible step. So basically this means that since I had the right mover, sort of I can merge this step with the next one and assume that this is executed atomically in one atomic section. So basically, this means that I removed, in some sense, some of the interleavings, okay? Because now I have less interleavings. Is this okay? So now, why did we did all this? Because now basically we can write the invariants that we need in order to prove the assertion. Okay? So now, what are we will use yield invariants. So now, what are these yield invariants? So basically we have one here. So, okay, so now before that, let me give you some intuition. You see, if I assume that this is done now in a single step, okay, so I have just, I can yield, a thread can yield only at this point, okay. Now you see what happens is that sort of every thread acquires a ticket and then he goes directly to the atomic section. So this means that I can no longer have two threads that have acquired tickets and sort of they are still pending. Okay. So now the interleavings are very simple. The thread gets a ticket, goes to atomic section, does the thing, then gets out, and another thread comes, goes to atomic section, executes, gets out. Okay. So the interleavings are much simpler. And this is why now this will be reflected now in the yield invariants that we in the assertions that we need to put the assertion. Okay. Because now this yield 2 here that holds all the time, so this is holds at every step, is that sort of now this T now, it's either the thread, sort of whatever that either everyone is out of the atomic section and only one can be in atomic section. And the thread T is basically all tickets up to S, excluding S. Otherwise, it's all tickets including S, if someone is in the atomic section. And we also have this other yield invariant, which is important for proving the assertion, which states that at this point, CS is different from null and it equals the value of the value of the ID. And you see here, there is an yield invariant with an argument. Okay? You see here now I'm calling this yield invariant with an argument, the thread ID of this particular thread, where I'm stating this. Okay?
So again,
Yes.
the meta question is, you had a comment about scalability. What makes it more scalable?
What makes it more scalable than Owicki-Gries?
Where are you? Like you have to do so many steps.
Yeah. But each step is conceptually, I think, simpler than writing Owicki-Gries proofs. So,
and I mean, it's also in some sense more generic if you want, because I mean, here, for instance, when we prove the correctness of this allocation of tickets, okay, in some sense, you can imagine that now this allocation of tickets is not necessarily T++, it can be whatever else, okay? Which can be, I mean, in this case, it's just T++, but you can imagine something more complicated for which you need a complicated proof and so on, that you can now separate from proving the rest. which is about once the it's
but I
That
want,
would appear in the Owicki-Gries group also. So you're saying you have to really understand your program well to,
yeah.
that I understand, but then that's not an argument for why this is.
So you are asking the question, why is it,
Why is it better?
why is it better than the classic Owicki-Gries
Yes.
tool? Okay, so, I mean, I think that you, on this example or in general?
In general. Yeah. What is
general.
it that,
I think in general, because you have to write less. And your invariant would be simpler because you have other strategies at your disposal.
although there is a mental burden on doing this refinement?
What, I mean, there is, what do you mean by mental burden? There is mental burden in writing programs.
Okay.
There is mental burden in writing Owicki-Gries proofs also. If you don't want to do any proofs, you want to do testing, there is mental burden in writing test cases.
But doesn't the scalability come from the fact that you eliminated concurrency,
That's not the,
right? I mean, you mentioned Lipton, but I think it would be nice if you explained what the effect is, right? That, and what's this concept of reduction, right? I think that if people have never heard about Lipton, it will, you say, okay, Lipton says, and then you have to believe it, right? Then it should be.
But I mean, I wanted to say that sort of these invariants, for instance, they are not true in the original program. I mean, for instance, this invariant that this set of acquired tickets is exactly this interval, this will not be true in the original. It's true here because I have less interleavings.
so is it right to say that Civl style proofs force me to think of these meta invariants?
For Civl style proofs will force you to, they try to mimic what informal arguments look like. Now, it is, it may not be easy to believe that somebody who invented the ticket protocol, the informal argument that that person would use would mimic this kind of proof. But I mean, most likely these informal arguments actually are not based on invariants at all. They are based on just saying, oh, look at this execution, it works. Look at that execution, it works. Oh, okay, it works. Something like that. Now, the only method I know of proving any program correct is invariants. Okay, invariants are not very fashionable because they tend to get very complicated very quickly. So the only chance we have of making invariants fashionable is to augment them with something else that somehow reduces their complexity. So I think that is all that is going on here. So it's just a matter of experience that there's a particular set of tactics that are there that seem to be helpful. So Andreas, so he has recently written many papers on commutativity. So he has become a huge fan of commutativities. So because of that reason, I think he wants to want me to make a stronger plug on commutativity, which I'm happy to do.
He wants you to cite it.
Yeah, that too. So commutativity, all the right mover, left mover business, it does seem to have a dramatic effect on the complexity of invariants that you have to write on the transform programs.
Yeah, has a question.
But my sincerest apologies for being late.
Yeah.
And I don't want to, I watched the inauguration of my new king instead of okay, so what is the underlying proof here? You already said that about
So it's like something like boogie.
it's something like Google.
Yeah.
Is it like what's it called? What you mean?
Civil, yeah.
Yeah.
Civil, yeah.
But it's something like Google.
Yeah, it's an extension of boogie.
Okay. Is your claim, I mean, there are two possibly quite orthogonal claims one could make regarding simplicity or scalability. There's runtime, okay, scalability, and then there is the complexity of specification.
Yeah,
Which one would you choose as your,
the latter.
the last, okay, so, so that's a different
notion of scalability, right?
When I really wrote
Typically,
the-
it's much
there
more.
is no, there's one more factor that you did not account for, which is this repeated refinements and coming up with these refinements.
Yeah, it's,
Like
But I
transforming
mean,
programs to simpler.
I mean,
That's
this
not
offers
easy.
you an alternative where, I mean, because you think like, let's say, core programming logics and whatever, I mean, they are basically, I mean, things are complicated. So then you state complicated things in logic, okay? Here it's an alternative where you sort of try to state some things in code and not logic, okay? But, I mean, it's an alternative, then it depends on what you like.
your claim is that your invariants become easier to state.
Yeah.
I mean, the logic part becomes somehow easier, okay, but you are doing this at the expense of writing code, meaning this abstraction sense.
Yeah.
So it's first instance the idea was that we're trying to reduce the amount of variants, but to
Reduce the amount.
this amount of the variants.
With the commutativity reasoning, yes.
Yeah, but it comes at the expense of showing that some actions actually occur.
Yes.
Correct. Exactly right. Yes.
And it's kind of interesting because you abstract, so you introduce
More,
more.
but it allows you to make a commutative. Yes, that's right. And the reason for that is also very obvious. So the thing is that invariants tend to get more complicated faster when you have a non-determinism due to interleavings, but they don't tend to get complicated as quickly when you just introduce relaxation of behaviors, like the kind of things that you do typically when you summarize the body of a procedure with a post-solution. This is again not heuristic, it's like an empirical thing.
No, I was just wondering, because you said your logic would be easier, but the invariants that you state are logic, those are your logic.
Yes. I mean, okay, anyway, I mean, this is always, it's hard to say what statement it's easier than others.
Yeah.
I mean.
But the abstractions that you do, so in the usual, in the usual techniques that I'm aware of, doing refinements and stuff, you do an abstraction and then you have several implementations. You do a refinement to make sure your implementations are satisfying the abstraction. Is that also the reason you are doing abstractions?
Okay, I think I know the question. I think what you're saying is that in the classical abstraction or refinement proofs, the proof artifact contains the simulation relation, and you are trying to prove that the simulation relation is inductive and whatnot, right? So your question is, where did that go? Why are you not talking about it?
Exactly.
Yes, it's a very, very good question. I'm glad you brought it up. We're not talking about it just because we don't. This is again, Civl is very different from classical approaches to abstraction and refinement, where it tries to hide the actual simulation relation that justifies a program transformation inside the logical machinery. And so the only thing it tries to expose to programmers are things like invariants and program rewriting and things like that. Although it is true that if you go look at the soundness proof of why all the transformations are correct, then you will discover that a simulation relation is actually being proved valid. To give you an analogy, if you have ever done a proof of soundness of a type system, right? You will find that there is a soundness theorem, type soundness theorem, which is this gross inductive invariant over the program state, which is actually what is getting proved, right? But the thing is that what the human user of the type system does is just plays with the rules, right? The human user is never never aware of that inductive invariant.
So your correctness is so the inductive invariant is done generically.
Is what?
It's done generically.
It's done there. Yeah, the underlying simulation proof is done in a very generic manner using the ingredients you supply from the outside. Exactly, like what happens with a
It's a meta theorem.
yeah, exactly. Yeah.
Also because, I mean, here it was not visible for the moment, but it will be when we will sort of translate this to Civil syntax. We are talking about structured programs where you have procedures and so on. So then all these annotations, there could be past previous conditions and so on. We never have access to global sort of configuration and state simulation relation of some global things.
Yeah.
Okay, so your answer was actually what I was hoping to find, but I think so you're basically automating the refinement that you
Yeah.
have to do normally.
Yeah, exactly.
And what you kind of have to, or what you require is a more richer, say, semantics of the program that you're actually trying to refine. And these are your invariants.
Yeah.
I have another question. So the whole time I was wondering why you go for this Owicki-Gries thing instead of some separation logic. And I looked this up because I was aware of what it is. And the first paper that I found was actually talking about this being not sufficient for weak memory models. So it's inconsistent actually.
Yeah.
So, and you're trying to use that as a logic to specify database systems, so basically inconsistent stuff like that. So this requires sequential consistency as far as the paper that I found, referring to. And would you say like so this is resistance that you're trying to verify target? It's sufficient for that. It's sufficient. Sequential consistency is sufficient.
I mean, you have to model basically your system into something that is consistent with the intelligence of this. I mean, even if you take weak memory and so on, you can always define an operational semantics, introduce channels, whatever buffers and so on. So then at the end of the day, the semantics of your program is just intelligent of small steps. But I mean, for distributed systems, for instance, you are required to do that. So you introduce channels and send and receipts will be like adding, modifying channels and so on. This will be like share state.
May I also leave with them?
Oh, so I want to add that. So whenever I hear sequential consistency, I remember that book from Owicki and Qadeer. And they had various levels until they reached sequential consistency. So there are more levels of consistency.
So
I was just wondering.
So I wanted to delve a little bit deeper in your question, because your question started with separation logic and ended with weak memory models. So I could see two distinct questions with that. The first question is, can any of this work with weak memory models? And the second question is,
No, so I was not actually asking that. I was actually asking if you are targeting applications for weak memory models or any of this. If you say no, then this question is answered very quickly. Right? I was just wondering because you were listing, let's say, very abstract distributed systems applications, say database system, your access is certainly an algorithm that's pretty damn complex, I would say. And I'm not 100% sure it relies on sequential consistency actually. But
when we talk about this distributed stuff, so here, at least many examples, most of the examples that we have now are like sort of protocols. So basically, where you have a set of nodes that communicate with some channels like F5 or that. And these are modeled in Civil as considering these channels as some shared data structures where you are allowed to insert or delete. And then the insertion and deletion in these channels, you can assume that is done sort of instantaneously. Because there are like the data structure, that symbol is introduced by the sort of interleaving on these data structures that they can grow and so on that represent the channels.
And your answer to my second question.
That was just very good. First question was something like this, that why is the starting point for your explanation Owicki-Gries as opposed to separation logic? Okay, and the answer to that question is that I was able to pin down what Owicki-Gries is, but to this day, I have not been able to pin down what separation logic is or what its starting point is. Because there is as many separation logics as the number of researchers.
I'm sure.
Maybe more. Maybe a person does very many times.
So the things that are not looked at, he's also very looked at. So we people like us, we have to go back to like at least things that have been around for 30, 40 years. And we can do that before we can claim that we really understand.
Yeah, the Owicki-Gries, I think, is probably the first one, so.
Yeah.
It's the first logic for concurrency, so. Yeah, but I mean,
it's a fair question.
No, I mean, it is a fair question and my answer is also very fair.
I mean, there are some
I
aspects.
understood it as being very fair.
No, but I mean, basically, it's not all about Owicki-Gries. There is also something that will see later related to linear types and so on that will
Yeah.
sort of model. or
But
deal with
linear
some of
types,
the issues.
linear types is almost as old as the Owicki-Gries.
Yeah, but they deal with some of the issues that you model with separation logic and so on.
Yeah.
So, yeah, I think we have to stop at some point. But you can ask your question.
You asked
not-
what you
No, I was just, actually, the question popped up in my head even without context, just because there's so much work that's been done there.
Yeah.
Okay, and it's, I mean, I haven't followed the details, but one intuition about what is somehow carving off the space of possible defects to the store. Okay,
Yeah.
and so I can, for example, use that sort of principle to say that this program doesn't touch this part of the store or the space. But that doesn't somehow enter into the way you think here. Is that because?
No, it does.
It does. Do you use other means of
Yeah.
carving up?
Yeah, there is like this linearity that.
So,
Okay.
let me tell you, you know, the most, the most basic way of carving things up is to give them different syntactic names.
Okay.
So if there's a variable X in the program, and another variable called Y.
Yep.
And they are stated at different places in the file, you know that you can model them as distinct pieces of store. This is classical for you.
Okay, framing does play a role.
Right. So
Okay.
I would say this, in defense of separation logic. It has had a remarkable influence on making sure that the community pays attention to framing. Before separation logic became very big, I think that framing was taken for granted. And it was kind of brushed under the covers because all we had was this kind of syntactic framing that I'm talking about. But this kind of syntactic framing is very restrictive, and there's a lot of important applications where it's just not expressive enough. And separation logic, to its credit, really emphasized. But in program verification, framing is just one of n concerns. If you spend all your time worrying about framing, who's going to pay attention to the other million things that you have to sort out? You see what I mean? So, having said that, framing is a very, very important problem, and it is, we are keenly aware of it. There is some machinery in place already, and more machinery will be added in Civil as we go along.
Maybe we can take a break here because it's time for a break.
Okay.
And we'll resume at 4.
Yes, both the work which
Yes.
okay, so you're not making, although the target of this review.
No, no, we fight both.
Yes, c'est un question. Je veux dire,
ça va changer absolument.
Oui. Ça
C'est
marche
le
pas.
seul endroit, c'est le seul endroit où la valeur de la c'est juste.
Oui. Non, mais
Et je trouve que ça serait logique, c'est vrai. Tu choisis n'importe quelle valeur et tu affectes n'importe quelle.
Ah, oui,
Parce
oui,
que de toute
oui.
façon, tu oublies le.
Parce que dès que tu viens obtenir le ticket, tu
Oui, si tu le, s'il y a par hasard.
So we will, we have a little bit more time.
Mais when you do,
And so, we're going here and, I'm around until,
Just-
et je suis que vraiment, si tu avais une spécification plus faible, que ça marcherait.
Mais si elle est plus faible, dans quel sens?
Mais parce qu'on avait dit que ça encode une ligne.
Oui.
Si tu utilises juste une ligne.
Et après, tu ajoutes ça comme variable auxiliaire.
Donc tu dois ajouter ça.
Ouais.
Et pourquoi ça marche pas avec juste qu'est-ce qui
En fait, à un certain moment, il y a une chose que j'avais discuté pour moi, encore, c'est l'histoire que les ID sont différents. Parce que tu vois, pour le moment, je triche un petit peu. Ces choses ne sont. Ça, c'est vraiment très important.
Yeah, yeah. So actually, I can show you that.
mais justement, mon expérience, c'était que je n'avais pas besoin de démontrer ça parce que la seule chose qui t'intéresse, c'est que
Oui, mais par exemple, si tu prends celui-là, cette statement here, comment tu prouves que ça discerne en interférence par rapport à ça?
I can show you, so we wrote this.
Il se peut que le trait ID, c'est le même aussi. Et donc, alors, à ce
donc, attends, ici, APS,
non, mais moi, t'as aussi à la fin, tu fais le.
ah oui, tu as besoin d'insurance freedom also from the statements.
So what we
Oui, parce que maintenant, ils sont comme des variables de ton programme, il n'y a plus de différence.
So, there is a, I mean, even this customer is part of the test wrapper. So this is enter. And
Donc,
this is,
intuitivement,
leave. These are the two library entries.
ce truc-là,
So we wrote
il,
this test drive. with the customer, right? The customer calls enter entry, non-conlusively, arbitrary number of times, while starting you just do it. Non-conlusive combination.
Sequential.
parce que
Sequential, but there is another thing on top, which is that there is this, main, so to speak, right? We just create
oui,
lots.
donc tu sais que
And it gives each
valeur
customer a
réussie,
criteria,
et
unique
tu sais
criteria.
aussi
So
que
basically, this is,
elle n'a pas
this is
utilisé
like
la ancienne adresse.
it's
So,
fine.
some
Et donc,
points, and
yeah.
each of them runs this, and
Ça doit se
some fine.
Et
Yeah.
si tu maintenant tu fais une séquence
Non, mais
So,
si tu
what we
raisonnes
do, yeah.
sur papier, sur les exécutions,
So he actually not.
et
do
maintenant,
anything
on a les règles
interesting,
de peu,
this,
comment
random
tu-
line.
tu-
The
cette chose, ça
interesting
diffère en
proof of
interférence.
was simply the assertion that
mais
Constantin
t'as
was
la
doing. We wrote this line,
c'est possible.
yeah, make sure
Il y a
that
des
there is no consciousness, that we
Oui,
have
mais-
actually prove
Ah,
a-
pour démontrer que c'est vrai. Toi, tu as besoin de...
But
Non, non.
if you have a good line,
Non, c'est juste
get a proof
montrer,
like
par
that,
exemple,
what will
celui-là.
end up happening is that supposing that you actually want.
Là, c'est ça que nous avons montré, que
So that
si tu prends ça, cette statement, et tu exécutes par exemple.
then what happens, that you have code of that thing also.
Et le reste,
And then what happens is that enter in, they would become.
non, cette chose-là se triple de voix. Et valide, c'est
And all the-
aussi le thread ID que j'ai là et le thread ID que j'ai là.
And then we will start doing whatever simple proof for the upper level things.
Qu'est-ce qui pourrait.
Parce que si elles sont égaux, alors la set est
Yes,
valide.
because there were-
Tu vas incrémenter et après tu vas accepter, tu vas faire le
Yeah, or if you have a sample
Et donc,
that you want, I can code it up to you and I can show it to you. We have samples like this also, like for example, there is a,
Non, donc tu peux pas utiliser que tout.
Yeah.
Moi, je suis toujours troublé d'utiliser le thread ID comme variable parce que est-ce qu'on sait automatiquement qu'ils ont tous des valeurs différentes?
non, ça c'est aussi c'est l'histoire de cette variable linéaire. Il y a un mécanisme
No, that is yet another thing.
derrière qui va
That is
justement
not
qui va
what
ajouter précisément cette
Well, it's functional for years.
Yes.
Yeah, that's
tu vas déclarer cette variable linéaire.
But I think that the technology is very different. Yeah. So they don't have the notion of layers that we have in Civil. They don't have it. What they're trying to do is they're trying to mimic layers using modules.
So what's the difference?
So the difference is kind of technical, it is actually,
Et donc,
you can make
ça,
a difference in the implementation.
c'est
So when
une
you are
variable comme toutes les autres, comme CS,
in modules are
et
functions,
En fait, c'est un paramètre
you
unique.
have to be semantics.
C'est aussi une variable linéaire. Même
And you
le.
have to make everything
mais c'est une variable.
Ouais.
The math is much more
Est-ce
complicated.
que
We never can give semantics to partial programs. Semantics is always given to a whole program. It's just that
dans mon
when-
modèle,
for that large program, instead of using such a way
dit,
that you can achieve these layers and
Bon,
break
Dieu, non.
pieces and so
et
on.
ensuite,
So, yeah,
il peut
like a classical type system.
update the list,
Then,
obtenir
and to, like,
une thread ID
situation where you have semantic markets.
qu'ils obtiennent pendant l'exécution.
Mhm.
Et ça, c'est ni une, c'est aucune des deux choses. C'est pas le truc qui est. Oui, donc.
Non, mais il était un paramètre du thread. Disons, on suppose que cette procédure, c'est tout ce que le thread exécute. Donc, il reçoit ça au début.
Mais quand pendant l'exécution.
Non, au début de l'exécution.
Donc, c'est. Oui, donc. Mais au début, c'est pendant l'exécution. Est-ce que l'attribution du thread ID, ça fait partie de l'exécution?
Oui.
C'est pas dans la précondition.
Non, non, c'est en fait dans le civil, en fait, quand tu écris toute la preuve et tout ça, il y a un sort d'allocateur pour le thread ID.
Il assure que les thread ID sont pairwise different et tu dois le montrer qu'ils sont pairwise different ou.
En fait, bon, ça utilise ces variables linéaires, etc. Et donc, d'une certaine manière, tu écris l'allocateur d'une certaine manière que c'est comme si tu prends par supposition qu'il te donne à chaque fois des valeurs différentes.
Je ne le trouve pas.
Oui.
Parce que, mon feeling, c'est exactement ce qui se passe ici. Hein. C'est comme si tu donnes à ces threads un nouveau thread ID. Hein, c'est comme le M et le thread ID. Et ensuite, tu fais le boulot pour démontrer que ce genre de thread ID est
Mais par exemple, ici, quand on a fait cette abstraction. So when we did this abstraction step, how do you prove this? Is you use this invariant here. Because basically you use the fact that all the time this t equal is exactly all values up to t, and you know when you get the next value, you get the current value of t and so on. So this is what allows you to prove that this holds.
You say this, I mean, this is the statement.
Yeah, this step that sort of you have to show that this is abstracted by this.
So this is the transition relation here. So what you do is you construct the transition relation of this step, and then you show that the pre-post states of this imply this transition relation.
So you need to show that this guy doesn't have less executions.
Yeah.
That's right, because then.
Yeah.
it would be easier. It's really deep stuff, right? I mean, there is so much going on.
Yeah, but the thing is, don't call it deep. It's very simple, really. It's very simple. See, the thing is that there is nothing here that you don't already know deep in your heart, which you haven't known for more than 50 years. It's so simple. Everything is very, very classical. It's just that we just decided we're gonna do things in the classical way and the simple way, which is very unfashionable, you see.
I don't get it.
How can something be more trivial than this?
No, but so what do you mean this? Do you mean the fact that the protocol is correct?
No. I mean, you were asking me, right? You say that there are a lot of moving pieces, right?
No,
But
no.
each piece is very straightforward, right?
No. I'm not saying no. What I'm saying is that somehow let me see. It seems to me like you prove the correctness of malloc. Yeah, because when I
No. I didn't prove the correctness of malloc. I think we proved the correctness of a client of malloc. Because malloc is like the ticket allocator, right? That is m equals t plus plus. And we actually proved the.
So to me, this has a little bit of flavor as if this thread here
Yeah.
gets a second kind of thread ID, which is here.
Which is our ticket.
Yeah.
Okay.
And now you are proving just when you, I think so. Constantin explained to me that when you have when you acquire the thread IDs, you postulate that they are pairwise different. You don't prove it.
That's correct.
Yeah. And here now you are going to prove it. You need to prove that all the M's that are assigned the secondary thread IDs that they are pairwise different. So there is something scary going on.
Oh, what you're saying is that I ended up proving a deep theorem. Somehow.
I don't know, but something scary, right? That malloc works is, malloc is really one of the original things of computer science, right? You don't have it in any other science. This business of pointers, of dereferencing, and so on.
But hang on one second. I'm still a little bit puzzled about what you're saying. So the correctness of that ticket protocol is a little complicated. I would say the invariant is complicated. But we know that invariant exists, right? Much before Civl. He was showing you an Owicki-Gries proof of that ticket protocol too.
So with this F.
Yeah.
And what? So did you use? Can you show us again the invariant?
Yeah, even there you need the fact that the three IDs are different.
Exactly. So
Yeah.
you show that this it's as if you had you need to you need to show this, right?
Yeah. So
Yeah.
even in this program, even in this proof, which is that you need the fact that the thread IDs are different. And you use that in proving all the invariants.
No, but I mean there are two things. So you know that the thread IDs, these things are different pairwise. And now you do an assignment where is the M gets T. And now you're going to show that, let me call it secondary thread IDs, that these are pairwise different too.
Yeah, that you're showing it by putting it in this map and claiming that it's a bijective map.
And saying that.
Yes, that's correct.
And,
Yeah.
and so,
So is your question that you are just shocked that we are able to do a proof without having this information explicitly in there?
no, you see, I'm just in this, where I'm not yet sure that I understand everything that's going on.
Yeah.
And my
But your fear is that there's something wrong.
No, not at all. But my impression is that in order to prove the correctness of ticket, you need to prove the correctness of a procedure like malloc, right? So for me, this is like a malloc, and
But this is, yeah, I mean, this was the purpose of this first abstraction that we were doing there. I mean, it's like this first abstraction step, it's like proving the correctness of this malloc that you are talking about.
Yeah.
This one.
yeah. So to prove the soundness of
Yeah.
it.
Yeah. But and the idea is that somehow once you first prove the correctness of this malloc, and then in a second step you do the rest.
And so I convinced Constantin that you can replace this by malloc.
Dude, are you sure?
Yeah.
Can you go back?
No, because I mean, you see now that this thing becomes atomic.
Yeah.
Okay. So now let's look here.
So let's
So now you execute this. Okay, you get an arbitrary thing and you enter the atomic section. Okay.
So if you make havoc here, right?
Yeah. It's like
How will you prove this invariant correct?
I mean, no, you have to rephrase that. Maybe you have to use again something like this T or whatever, something like this. That one will not work anymore.
But what is the proof now?
I mean, I think
You're going to give me some intuition or a proof?
no. Okay, let me give you some intuition.
Okay.
So the idea here is that you get an arbitrary ticket.
Yeah.
You go into the atomic section,
Yeah.
and then here you are saying, okay, I give the hand to the next one in this order.
Yeah.
In the next integer in my order. But I could, since these tickets are chosen arbitrary, I could say I give the hand to an arbitrary guy. I don't need to give the hand for the next one to enter that atomic section. Yeah.
It could also be again introduced deadlock because you serve somebody who doesn't exist.
Yeah.
I am not able to see this intuition. It's unfortunate, the only thing I understand are invariants.
Mm.
You give me an invariant.
And so you're saying the invariant changes.
Yeah, because it's here if you halve up this S, then you can go to a big S, then come back to a small S and so on. For this, you'll not have any more the single one.
Yeah, so we look at how this invariant is being proved inductive across here, right? So this is setting CS
Which
from
invariant?
this one.
Yeah.
Proved inductive across this assignment. This assignment is in right? And it is setting CS to nil. So, and before that, CS was equal to TID. So we were in this situation. We increment S, and now we have to prove that this situation holds. Now T did not change. Right? Capital T did not change in this assignment. So the reason it works out is because I incremented S by 1. That's how I know that I moved from this situation to this situation, right?
But yeah.
And so what do you need yield 2 for?
What do I use it for?
Yeah.
I think that what you really need is this guy, right? Because without this one, you can't prove this assertion. And I think this guy by itself is not enough. So it needs this one. So now let me try to see where you need that guy.
I mean, I think it's some interference check. I mean, to show.
So, okay. Okay, we can go through it later. I know the question you're asking, you want to know exactly where the stack is getting used. I will look into it again and I will tell you.
Because t was minus infinite to t, right?
Yeah, before.
Before,
Yeah.
Now there is no more t. Small t.
we changed.
But you can back.
The proof would be more elegant if it didn't use the complete value of CS, because the S is still linked to the T, right? So in a way, the T is still around the small t.
Mhm.
But then I assume that we need to use some analog of this big capital T to store what are the tickets that were served. To say that you pick a value to serve a ticket that was not served before.
I got you one more. Then the-
One more,
Ah.
thank you.
Hello.
Good to see you again, Lauren. So, finally, in the.
Hello.
That's,
Yeah, thanks.
It is session review.
Yeah, so I'm going to do that. So.
But really, for people that
So
don't get in the middle somehow. I know.
Leave that talk and I will share with all.
Yeah, I mean, maybe I will do a small review at the beginning. And,
I know you not have to.
So what I want, I don't know, a very strong blood for working. Right? So if somebody wants to partner with it,
I didn't say
And that's usually the main conversation.
by the way, I think everything that we talked about in the break was recorded. So
Oh, I see, okay,
anyway.
all right.
So I guess okay, let's wait one more. Thanks. Yeah.
So you're the king of Denmark, got coordinated.
Yes, and the Queen Margaret II.
How could they allow that even happen in your house?
That's a very flattering question.
What is known as a rhetorical question. It was a rhetorical device. My wife uses it on me all the time.
No, she actually quite surprising.
I see. I see. So the son is I see.
Okay, so I guess we can resume. So I mean, before the break, so we were discussing the proof of this ticket protocol in Civl. So we have seen that basically from the original code, we can define a level of abstraction where essentially we introduce auxiliary variables. Then from that level of, from that abstraction with this ghost code, we can sort of define a proper abstraction where instead of saying that we acquire the next ticket, we say that we acquire an arbitrary ticket. And once that was not used before, and once we do that, we can something becomes a right mover, we can have an atomic section, less interleavings, in some sense simpler invariants, or like anyway, the behaviors at least conceptually are simpler compared to the original code. And now we are at this point. So we are using these two yield invariants, so there's annotations in the code. And as I was saying, I mean, these annotations, like in any Owicki-Gries proof, they must satisfy non-interference. I mean, actually, for the moment, I was cheating a little bit because actually it's very important that, I mean, at least this non-interference proof holds only if we assume that sort of each thread gets a different thread ID. Okay? And to see that, I mean, to sort of specify that in the proof, we are going to use this linear type system of linear variables. So basically, these are variables that store values that cannot be duplicated. And then there will be a type system that will ensure implemented in Civl that will ensure that these values are not duplicated. And sort of we can then assume this distinctiveness of these joiners, we can assume it in the verification conditions. Okay? And basically, if we think about this thread ID business, so we are going to declare these thread IDs as linear variables, so then they cannot be duplicated. And it's sort of, in some way, we are doing that in order so that when we sort of talk about non-interference checks, to sort of be able to say that I'm checking non-interference for some assertion in some thread I with respect to actions of some different thread J. Okay? And let me give you an example. So if we take this invariant, which was saying that this goes variable is different from nil and equals the thread ID. So I want, for non-interference, I have to prove basically this whole triple, that if I take this assertion, I execute this action that was defined somewhere in the code where I have this assert and increment, blah, blah, then this assertion remains true, okay? Now you can see that basically this whole triple, if I assume if this thread ID here is the same as this thread ID here, doesn't hold, okay? Because basically, if they are the same, then this step will sort of turn CS to nil. So this means that it cannot be, I mean, it will invalidate this thing here, okay? But if we assume that they are different, okay, then basically this assert will fail and it will not change the state. So then the assertion will still, the annotation will still remain true. Okay? And basically, as I was saying, how we do that is sort of, I mean, we will see syntax very quickly, but basically in the yield invariant, we can declare that some arguments are linear variables, okay? And also this step here will be represented as an action, which you can think of it as a procedure that executes in a single step. Also having an argument, having this TID as an argument, which again, we will say that it's a linear variable. Plus, there will be at some point in the initialization code of the program, something that will ensure that these thread IDs are really different from one another. Okay, so now, all this was sort of abstract at the level of pseudocode and so on. Now I will show you how to write this effectively in Civl. Okay? And basically I mean, as we have seen up to now, so we had several layers of abstraction. So we started from the original code and did at least 2 layers of abstraction, okay? So basically it means that even in Civl, I have to write different, what we call layers, okay? So now I will show the layer 1, which is basically the original code. And I mean, also for, let's say, I mean, to somehow, let's say, write code which is closer to the implementation. Now, in some sense, I mean, you see there is, this is written in a sort of not pseudocode-ish style. So now I have procedure, I don't include, include code in procedure, for procedures and so on. So this is also to show that basically all this can be, that Civl is not about just pseudocode. It's really about real programs. Okay, so now if we think about layer, so now basically each layer in Civl, I mean, at each layer, I will have some number of variables. As you saw at some point in the abstraction, for instance, this small t disappeared at some point. Okay? So it means that really, I mean, variables don't exist throughout all layers of an abstraction. At some point, they may disappear or they may be introduced. Okay. So the first layer, I just have the original SNT as shared variables. And then I will have a procedure main that will spawn a number of threads, each thread executing this ticket protocol. Okay, so I'm doing this async call. So this is like spawn thread that can execute this procedure. And then this procedure, it's in a loop try to do this procedure enter, which is really about acquiring ticket and waiting that it's his turn, and then leave, which is about incrementing this as +1 and getting out. Okay. Now, you see that, I mean, there are this annotation with whatever. So basically here, these are things, I mean, in Civil, you can specify that a certain variable or a procedure exists at a certain range of layers. Okay. So for instance, this variable T you see exists only in layer 1, because as we said, at some point disappears. The S remains up to the end in layer 2 as well. Okay. And then for procedures or atomic actions, you have the same. Okay, I didn't talk about atomic actions. So here, so you see here in the code, I have regular procedures. So these are really standard code. And then I have these atomic things, which are really actions that execute in one step. Okay? And there's syntax, you see I'm using usually call for procedures and exact for an atomic action, just to distinguish. Yes.
Where does the ID come from in the name?
This one?
The name, yes.
Thread ID.
Where does it come from?
I mean, there is some part here which I ignore, which is sort of something, some code that will allocate the thread ID values. Okay. But yeah, if you want, I can show. Okay. Now, we were doing abstraction. Starting from this original code, we want to do abstraction. So one part of the abstraction was to introduce some ghost variables. Okay. And for instance, here I wrote precisely the code that you can use in Civil. For instance, here to say that T now gets updated with, I mean, we represent that by the characteristic function. So then we update the set to say that for this M, that M is included in the set. Okay. And then updating this CS to say that it gets the value of TID sample. Okay. And yeah. Okay. So basically, this is sort of this syntax with call and whatever. It's used to introduce new variables. Okay. And you see, these variables are introduced at this layer 1. They don't really exist yet at this layer. It's just that sort of they are introduced in a relation to variables. Their definition is related to variables that exist at layer 1. Okay, but themselves, they don't exist yet at this step. Okay? And now we can also say that some procedures, okay, are refined by some atomic actions. Okay? There's a method of abstraction. Because for instance, here, I mean, if we get this one, I mean, getting the ticket and updating this ghost variable, of course, this ghost variable, we just introduced it and it's modified only here. So it means that we can assume that these two things are done actually atomically. Okay, so we can prove that these two are done in a single step. Okay. Okay, so now we are at this layer, we define the variables that we introduce in the next layer, the ghost variables. And also we state the abstraction in terms of some procedure being refined by some atomic action. Okay? So now in the next layer, those procedure calls would be replaced with calls to these atomic actions that were their abstraction. Okay? And this is what happens here. And now you see also something that, of course, is that now basically we can show that this step where we were acquiring the ticket that was not used before, now it's a right mover. So this is syntax in Civil to say that something is a right mover. So of course here we specify it, but under the hood Civil we really check that this is really a right mover. Okay. And also what you can see is that since here, I mean, you see like usually in Civil, I mean, there are like, we always talk about cooperative semantics and preemptive semantics. The preemptive semantics will sort of yield a thread at every sort of control location, okay? Now there is a cooperative semantics, which is specified by sort of stating yield invariance, okay, calling yield invariance, you see. And the fact that here I didn't specify, didn't annotate this point in between these two atomic sections, it means that actually I'm saying that this should be an atomic section. And this under the hood will be checked by Civl, and it will be based on Lipton's reduction, the fact that this first step is the right move, and then he sees that that thing becomes an atomic section. Okay, and now, so, and you see at some point you also have this asset, which is related to the specification, proving mutual exclusion. And then in Civl, there always exists an implicit layer in some sense, which is doing nothing and has no variables, okay? But, and now, if you think about, so now with this implicit layer in mind, Civl will try to establish that this is a refinement of this layer that does nothing, okay? But doing nothing implicitly means also that you don't fail. Okay? So in that sense, proving that this layer 2 is a refinement of this layer 3 means that you have to establish that this asset never fails. So basically, this everything, in some sense, everything about proving correctness in Civl is reduced to a refinement question. Okay, now, basically this, everything what I presented, okay, there is also something, okay, let me give it, try to give it quickly. In Civl, basically you can never call explicitly an atomic action. Atomic actions are just artifacts of specification that are introduced for layers and so on. Okay. You can only call procedures. But now at some point you have to start, I mean, there are some basic steps in your computational model that you have to specify what they are doing. Okay. So there is always in a Civl proof, there is always a layer 0, where basically you have some procedures like this. Yeah, I'm showing it here. So you have some procedures that have no code, for which you specify an atomic action that represents an abstraction. So in this sense, in this layer 0, we are specifying the primitives of our computational model. And I mean, there is basically no, I mean, the fact that they have no code trivially implies that they refine the atomic action that you specify yourself. Okay. Okay, so now this was, okay, and then, so basically this is like sort of the layer 0, where you specify the atomic action that define each procedure. Okay, now basically what I presented now was something, it's like a Shugler variant, okay? Because you see, I mean, you don't, I mean, if you would have to write all these 3 different layers, I mean, you have to write this procedure maybe 3 times, this one 3 times, and so on. I mean, you don't have to do that, okay? So
zero is
the what? This sharp 0, yeah, it's sort of, I mean, it's just a convention.
It's just a name. It doesn't have any semantics. It's just a convention.
Okay, so basically now you don't have to write these layers one by one, okay? Basically the program that you write in Civl, you sort of write all layers all together, and if a procedure is sort of used at different layers, you just specify the layer range, okay? And the convention in Civl is that you specify only the disappearing layer, sort of the layer until which the procedure survives, okay? So in this case, the main will exist at all layers up to and including layer 2, the customer up to and including layer 2, and so on. And for variables, it's the same. Okay, you specify the range of layers at which it exists. Okay, so you see that, for instance, this T sort of exists only up to layer 1, this S up to layer 2, and so. Okay, some variables are introduced in the last that they don't exist from the beginning. Okay. And now basically think in layer what in Civl what you write is a sort of merge of everything that we have seen in these three layers. Okay, so you have this procedure enter that exists up to layer 2, and then you have the get ticket that calls this get ticket at layer 0, but this is abstracted by some atomic action that exists up to layer 2, and so on. Okay, now everything is merged. I mean, you write all procedures and you always state up to which layer they exist. And basically now it's just the merge of everything that it's not. Okay. Now let me say about I didn't to present something about the syntax of yield invariants. Yes.
I think the question was answered here, but this business of everything that is proved as a refinement.
Mm-hmm.
Why?
Why?
As opposed to?
I understand that if everything reduces to one thing, it's nice if you're in an algorithmic framework, but if a human has to do it and something is hard as a refinement and I want an easy way out, why should I be forced to do everything as a refinement?
No, it's not true. No. I think you misunderstood. When you can have a large program and you don't have to do refinement, you can just do a one-shot proof. Maybe that's what you're asking.
But I mean, I was just quoting Constantin, maybe he didn't mean it the way he said it.
So are you talking about the one where he was talking about the skip action?
Yeah.
No, so what you can do
I mean,
is.
not just that specific thing, but during that bit, he said something like in Civil, everything that you prove is a refinement.
No. So yes, that is true. That is true, but that should not make you happy, but unhappy. Because the thing is that you can have a very large program with many procedures, okay? And you don't have to write atomic action specification for any procedure. Don't just write an invariant, and basically what it will do is it will make sure that the invariant holds everywhere. And it will prove that every procedure specifies the skip action internally to make sure that all the assertions are verified. You don't have to worry about it, but it's basically a classical invariant proof.
I mean, this last step of proving refinement of skip, it's essentially proving that every assertion is satisfied. I mean, it's nothing complicated that you should think, this is.
So you don't have to convert everything to an atomic action. You don't have to. It's up to you how much you want to do all this nonsense with refinement and so on. At some point you can say, I'm done with this. Now I just want to do a one-shot invariance-based proof. End of story. Yeah. So to the point being that it is a very important design goal that nothing that you are used to will ever be taken away from you. Every proof that you are able to do, you should still be able to do, and some more. So you can have a Civl file in which there are no modes. There is no refined algorithm. Still a valid Civl file.
And so.
But then the invariants that you have
Aim
to
to
write.
translate the Owicki-Gries discourse to like a direct.
And Owicki-Gries proof is just
Already
such as is.
Yeah.
Yes.
Okay, so now something a little bit about the syntax of this yield invariance. I mean, I showed the keywords already and so on. It just that now I just want to be clear. So now this yield invariants also have a layer. Okay. Because for instance, we saw that there was some, yes.
Sorry, can you clarify again what it means? You have a phrase and so for the variables.
Yes.
It kind of looks like T is not present in layer 0.
Yeah, because at layer 0,
That's the skip layer thingy.
yeah, this layer 0, it's like because you have all this, you are introducing all these procedures that have no code basically, and then you show that, so this was layer 0.
Nice.
So basically you show that these procedures are refined by something, okay? But it's only in this atomic action that you have the variable, okay? Here there is no variable, actually. At layer 0 is just some polygon procedure.
But it should look like enough
closed intervals, or like not including the left side and including the right side, or is this thing?
Yeah, I mean, this is related because in Civil, you would specify these two bounds in this way. So you specify the bound at which the variable is introduced, okay? In the sense that you give a definition that depends on variables at that layer, okay? But the variable itself is not used in computation and up only at the next layer. Okay? And here is the variable where you introduce it, and it's open because it doesn't really exist there. It's only defined. Okay? And then the other one is where it is.
Yes. What is it? Is it like?
Here it's like minus infinity, just that you specify only the upper bound at which a procedure disappears. Otherwise, it exists from layer 0 up to the one that you specify. Okay, so yeah, these yield invariants also have a layer associated. For instance, you remember this small t will disappear at some point. So whatever invariant we had exists only at layer 1. Okay? And then at layer 2, we have the other two invariants we saw. Okay? And then basically you can sort of, whenever you need them, either as preconditions or to specify assertions for when you have yield points, you can just simply call them. So here I'm giving an example of what would happen in main. Then, for instance, in customer, in between the acquiring the ticket and leaving the atomic section, then you will have to specify the yield invariants that follow.
Can you write something that relates to variables on two different levels? Can an invariant belong to two consecutive layers?
No, I mean at the moment it's they are specified layer by layer.
But it is true that sometimes I've seen cases, they're not very common, where you end up using the same invariant as multiple layers. So I've been thinking about associating yield invariants with a set of layers as opposed to just a single layer. It might be handy in some situations.
No, I was thinking in some sense you're sort of breaking down this refinement relation to facts on the two different layers, and then you're reestablishing refinement based on these invariants as guidelines, let's say. But if you could actually relate them in the invariants, then maybe the refinement would
So there is,
be more explicit in some sense of the word.
if you have multiple invariants for multiple layers, then that means that there are multiple refinement groups, one for each layer, and they're all done separately. Just as a clarification. Now ask your question again.
So if I have invariants for layer n and layer n plus 1,
Yeah.
when I'm trying to establish refinement space, a refinement between the two layers, it's sort of my job to use the invariants to then establish that refinement, right? But if I had something relational, I mean, I don't have an example to. It just says that it could be more useful in actually establishing that refinement.
But if it's relational, it means that you have new variables at layer n plus 1.
Mhm.
But those, when you define those,
Issues
when
that
you
I could have, right?
yeah, but when you introduce, I mean, that variable basically you are defining it at layer n in function of variables that exist at layer n. So it's already relational.
Also, you're saying that definition is sort of the.
Yeah, the relation.
Yeah, we already have that. It's just couched in explained in a different way. It's not explained the way you are explaining it, but it's there. And in fact, it's very important. Your intuition is absolutely correct.
You see, like, for instance, when I'm defining this t here, okay, but I'm still using the m. But I mean, it's still, I mean, this is a new variable, okay? And it's the set of m's that exist at the, whatever, previous layers.
So if you introduce some variables at say layer 1, right? The invariant that you would write for layer 1 will include the variables that already existed at layer 1 and the introduced variables. That's very important. Yeah.
Okay. Okay, so this was yeah. So about the invariants and
Okay.
now it's your
All right, I shall use this here. Just click this. Okay. All right. Okay, so there's a lot of material still here, but we're going slow, and that's absolutely fine. We don't have to go any further than there is time for. We'll go as slow as we need to. So what I'm going to talk about here is, Constantin showed you earlier how we model distinct thread IDs using permissions and using a linear type system. The example that he used was fairly straightforward. You just had a thread ID that was passed into the top level procedure of a thread, and it just kept getting passed from one place to another, and we were not duplicating anything. So there was not that much complexity, conceptual complexity, but sometimes there's more complexity to permission management. Sometimes you have to take a permission which is a bulky permission. It's contained in a variable, and you have to split it without any duplication into two variables. Then you pass off one variable over here, stash the other thing over here, and then later recombine. So I have some examples motivating this, and I want to show you why, how we deal with this. The thing that I'm about to show you is very deeply tied to the business of ownership transfer. So ownership type systems and dynamic ownership chain, these are problems that are studied classically in lots of PL papers about it. What I'm talking about here is very much related to it. Okay, so I motivate this issue of permission redistribution using this example of barrier synchronization. So in barrier synchronization, the idea is that you have a bunch of threads, and there is some other supervisor that every once in a while has to do a critical operation that require all those threads to block. So the supervisor and these threads, they have some kind of coordination, which is barrier synchronization to achieve this. So it's almost as if, these threads, every once in a while, they check whether the barrier has been raised. The barrier will be raised by the supervisor. If it is raised, then they block. And they let the supervisor know that they have entered the barrier by blocking. To do that, they decrement the counter. The counter is initialized to the total number of threads. When the counter becomes equal to 0, that's when the supervisor knows. If the supervisor is waiting on the counter becoming equal to 0, that's when the supervisor knows the threads are truly blocked. It goes ahead and does that critical operation, and then it releases the barrier. So the waiting threads are just waiting on the barrier variable, and then they see the barrier raised, they go. Okay, all right. So that's how those are the primitives that I've shown here. So this is the barrier on variable, which is ordinarily false, and when the supervisor wants to make these threads enter barrier synchronization, it sets it to true. Okay, so and when a thread is entering the barrier, it decrements barrier counter. So the barrier counter is initialized with the number of threads, and then it waits until barrier on is set back to false. When it is set back to false, then it increments the barrier counter and goes on its business. So eventually, again, all the threads will leave the barrier, and then the number of the value of barrier counter will become equal to n, the number of threads. Okay, so here I'm using the phrases mutator and collector because this example was originally inspired by a concurrent garbage collector. And this supervisor is this collector, which every once in a while has to do a root scan. And somehow it's very important that the threads are not modifying the roots at that time. So it has to block it. And threads are called mutators here. So typically, they will enter the barrier, exit the barrier. Here they will be accessing memory and roots and whatnot. And so as long as they're waiting over here, it knows that the collector knows that memory is not being changed. And the collector, what it will do is it will set barrier on to true. It will wait until barrier counter is equal to 0, and then it will do the root scan. And then when it is done with it, it will set barrier on to false. All right. Okay, so let's prepare for a local proof of this, using the kinds of things that Constantin has been talking about. So the first thing we'll do is we'll introduce some state, because typically we tend to do that, right, in creating local proofs. So here we added a barrier set. This is a set of threads that are currently waiting in the barrier. The intuitive invariant in our minds is that the number of the size, the cardinality of barrier set, plus the current value of barrier counter should be equal to n, a number of threads, something like that. So here we expanded enter barrier and exit barrier to do the appropriate operations on barrier set. So when you enter, you add your thread ID to barrier set. When you exit, you remove it from the barrier set. Okay. So far, so good. Any questions? Okay. Now, I'm not going to bother with telling you what the golden specification is in this case. I don't want to do all that setup. I will just jump straight to an invariant and pretend that our only goal is to prove the correctness of this invariant, which is very intuitive, okay? So what are these invariants that we want to prove? There are two invariants, mutator invariant and barrier invariant. Let's first look at the barrier invariant. Okay, so barrier invariant is saying that it's the invariant that this collector would like to have true, would like to know to be true at the point where it's doing the critical operation, right? So at the point where it's about to do a critical operation, it knows that barrier counter is equal to 0. So it would like to know that this fact holds, because if this fact holds, then this means that barrier set is equal to n. So it knows that all the other guys are truly bought, and it's really safe for me to do the critical operation. So that's what this is saying, barrier invariant. And this mutator invariant is doing something very, very simple. It's saying that, okay, well, I just added myself to the barrier set, and I know that later I have to remove myself from the barrier set. Clearly, I don't want somebody else to remove me from the barrier set. That would be very stupid, right? So it's just calling this mutator invariant here, which is just saying that the fact that I'm in the barrier set is stable. Okay? All right? So now, these simple things we are not going to be able to prove, because if you look at this mutator invariant, let's try to prove that it is preserved by exit barrier. Okay? So let's say mutator invariant is being asserted by thread J, and exit barrier is being done by thread I. So because there is no constraint between I and J, I might as well be equal to J, and it will remove it from the barrier set. No, not good, right? Not good. Okay. And there is a counterexample here also for barrier invariant. I mean, here the situation is even worse, because barrier invariant doesn't even have a parameter, right? So barrier invariant is not going to be preserved by enter barrier I for any thread. Why is that? Because let's see, why is that? Enter barrier is over there. It can decrement barrier counter.
I is already in this.
I is already, it's imagining, it's hallucinating that I is already inside barrier set. Okay, there you go. All right, screw. Okay, so now we are going to use permissions in a more sophisticated manner to be able to rewrite the program so we can prove these invariants locally. Okay, so we will have thread identifiers which will look a little bit more sophisticated.
But why don't we just add these conditions?
I add what?
These extra conditions.
Which conditions?
I is not.
But that is what I'm going to do. So,
For that you need linear types?
Yeah. I mean, so the thing is that there are many, so the thing is you can always do these things, right? You can add those variables up the wazoo and get the proof done. What I'm going to show you is one particular way of doing it. That's all.
Add y.
Huh?
We should add the y.
Why?
Why your way?
Why my way? I mean, that's almost like an axiom. in a way, I'll tell you the number one reason why. Is because I have failed. I have failed literally at all past attempts. The thing that I am describing to you is the only way in which I have achieved even the least amount of success, which I'll tell you is nowhere close to enough. That's the only reason. So you have to, there is nothing, this is not the final word. This is just my personal experience.
You have gotten much more philosophical than this example now.
Huh?
You have become much more philosophical than this example. I think Oman was asking why not add the conditions.
Which condition?
The I not equal to J over there, right?
How do I add I not equal to J? I and J are not in the scope at the same time.
But okay, I'm not I in J, but let's say I say I is not in the barrier set, then I do the entire. So
You mean this one or this one?
I guess
Left.
yeah, left.
This one? This one I can't do because I and J are not in the scope at the same time.
This is some non-interference check. So if I have some.
I and J are different threads. Where will I write this to you? I not equal to J.
I understand that this check is arising from the Owicki-Gries non-interference.
Yeah.
You cannot add the condition.
This one, maybe there is some possibility.
So then.
But the thing is that I have to solve both of them, right? Why not solve both of them in the same way? Why invent two different things when I can get to, make it with one?
So like, we're talking about inventing those variables in the sense that you would invent those variables or bring one in the context of the other. That's what you meant.
Right. So no, it's not. No, it's not like that. What we will do is we invent a mechanism for introducing ghost variables. But those ghost variables will enjoy a certain invariant that is known, so that the verification condition generator, when it generates the non-interference conditions, injects that invariant automatically in the background. If you just write ordinary I and J, there is no justification for putting that assumption I not equal to J here. You either have to prove it, you have to prove it's one way or another, right? So how do you bootstrap this thing? That bootstrapping is the only thing that this linear type system provides you in all this permission business. Any other questions about this? No? Okay. All right, so what we are going to do here is that we are going to add more parameters here. So we will add the thread ID just as before. But my thread ID is not going to be linear, unlike the example that Constantin was showing you. Instead, I have some other funny parameters here that are going to be linear, and they will bear a relationship with this thread ID. Okay, so let's, to understand these other variables, I have to show you what their type is first. So there is a type called perm. It wraps a thread ID. It provides, there are two variants, left and right. So it can wrap a thread ID even either using the left variant or the right variant. Okay. So the idea is that you can have, if you have a left V and right V, they are individually linear values that cannot be duplicated. But if you have a thread ID, which has both the left half and the right half, you represent it using the set containing left eye and right eye. But then you can split it into two different sets, one containing left eye and one containing right eye. Okay? And what we can now do is that we can put, we can make barrier set a set of these permissions. So what we will do is, when a thread comes in, it wants to enter the barrier. It will split its thread ID into two parts, and it will stuff the left part into this barrier set, and it will keep the right part to itself. And then when it gets to the exit barrier, it will remove the left part from the barrier set, unify it with the right part. Now you have the full set of permissions and return it. And it's very important to do this unification again because these mutators may call enter and exit over and over again. So you have to return them in the same state. So this is the magic basically. And you can see how, this can help now. We can walk through the proof. So enter barrier, it takes in both halves of the permission. It says the right thing about, connecting the value I with those two variables. And it also says that this thing is in. In means that you're going to lose this permission. You're going to lose it because you are going to add it to the barrier set. That's the non-duplication part. If I did not put in here, then the BC generator will complain that you are duplicating permissions. Okay. And then on the exit barrier side, here it says out. So here the idea is that this variable here does not have the requisite permission at entry, but it will get it when you exit. And the reason you get it is because you are removing from barrier set and putting it into that variable L. Okay, so now we can look at mutator invariant and exit barrier. The non-interference condition. So mutator invariant, because we have given the left already when we enter into the global variable, this one will say left j belongs to barrier set and r arrow val is equal to right j. Okay, so now when we try to prove that it is not interfered with by exit barrier, why does the proof go through? Oh, it's because the right half is present in both mutator invariant as a parameter, and it's also present in the exit barrier as a parameter. So you get a contradiction because the two have to be distinct from each other. Okay. So this is how we encode the fact that a thread that enters the barrier is the one that exits the barrier. Okay, the second one is, let me finish this and then maybe we can go over, why this and why not that kinds of questions. So let's say that we have a barrier invariant and we are entering the barrier, right? So here the counter example that we were imagining was that the value was already in barrier set. But notice that if here both these permissions are there, right, in the input parameters of enter barrier, right? But so this would mean that barrier set is disjoint from left eye and right eye. Okay. So this means that I cannot be in the barrier set, right? Because if it was there, then we would have left eye, some left eye prime there, but it's disjoint from this left eye, so it cannot happen. So you get a contradiction. Okay. So this is the story. Now, do we want to chase this thing down, or, in terms of,
It's okay.
You're comfortable with this? Okay, he's comfortable. Are you comfortable?
I'm not at all confident.
How about you? What's your level of comfortable?
I am in two minds. In terms of the correctness of what you've explained, I think I'm comfortable.
Yeah, that's because you trust me.
That's perfect, brother. But
Now, that's the case. That's a different story altogether.
the thing that makes me maybe a little uncomfortable has to do with the subtlety of the machinery that has to be added to
Yeah.
the basic code in order to be able to express the truth. And I was wondering if, for example, it would be possible to give a logical statement that I could sort of more easily understand, and then maybe derive this as a kind of implementation.
Yes.
The
So that-
logical instrumentation that that statement would give rise to. I mean, with this example, you leave me a little bit thinking that that it's getting pretty subtle, and it's getting the distance between the code that's actually acting that's solving my original problem, and this one is getting a little big.
I know.
Okay? Because, you know, why happens to have some,
So let me ask you this question. Why did you not ask me exactly the same question before this, when Constantin was telling you that the proof of correctness is going to be arranged as a layer of n programs, and all those programs have to be proven correct in order for us to conclude the correctness of the lowest fair program? Why was your skepticism detector not finding at that point? Because that's also a very, very elaborate argument. Why is it finding here?
I think it may have to do with the fact that before the multiple layers, if I'm remembering correctly, had kind of like an abstraction block to it.
Yes.
Okay, whereas here,
You don't know. Okay, now I understand the crux of your question. Now I understand the crux of your question, and I will try to address it. I'll tell you this.
to program
Yeah.
completely different structure
Yeah.
into the program that I can only relate to by, you know, having some very subtle ideas about.
So here, the machinery for relating to programs is inherited. There is nothing new here. The only new thing here is all this permission nonsense. Okay, so then what is the crux of the logical argument for the permission nonsense, right? Let me argue about that. It is invariance, nothing else. All that is happening here is that there is a global invariant that can refer to the entire state of the program, all the threads and all the stacks and so on and so forth. And it's a very strong invariant that has to do with this linearity business. That invariant is being established separately from this abstraction machinery. And these assumptions that I am injecting into my verification conditions are simply pieces of that invariant. This is what it boils down to.
I mean, just if we think about alternatives, I mean, the only alternative that comes to my mind is to have like some auxiliary variables that store the control point of every thread. And then you have a beefy variant saying, okay, summing the thread is at this control point, then the other one cannot be at this other control point, and so on. So all this machinery with the permissions and so on, it somehow encodes this invariant that talks about the control points at which different threads can be in different configuration.
I mean, I guess something you start thinking about if I were to try to really understand every detail of this, is that I would start thinking about how to relate this left-right business.
There is no,
We need to come in like a Deus ex machina somehow, and I would like, it triggers in me the desire to understand where does that idea come from, and in terms of some maybe some more powerful logical statement that you might be able to formulate if you imagine that you had a God's-eye view of the entire system, for example.
yeah, so,
You see what I'm saying?
I mean,
Maybe it boils down to framing, and maybe that would make me happy if, for example, there were some kind of way of explaining how do you arrive at this idea? And maybe if the explanation is, oh, but this is just a way of expressing the frame.
this is, no, but this is not a new idea. This is very classical. If you look at the permissions literature,
Okay,
this fractional permissions.
okay, fine.
So
Okay, fine.
you might as well lay this complaint at their doors.
Okay.
This is just, I just,
Well, but this is already good. I mean, this is already making me.
this is just an encoding
Okay,
using, techniques that are at least 40 years old. How old is linear analysis?
Yes. I think, I agree with you, but I think that problem was solved that way because exactly like you, they were insisting on whatever we call a local group.
Okay,
You force a local group,
yeah,
and then you need the global invariant,
True.
and then you need this sort of sophisticated way of pushing your global invariant.
sure.
So why? Why do I have to do it?
It's just one alternative. You don't have to do it. If you,
But I mean, this, look at the original code.
yeah,
It basically uses integer counters.
yeah,
As your first time you're introducing sets,
yes.
then everything becomes complicated.
Why?
Then- Because, I mean, the person who actually wrote the code,
Yeah,
are they thinking about sets? Maybe yes, maybe not.
maybe not, yeah.
So, I mean, sets are complicated. Now you have to deal with the sets.
So,
Now you need all of this
I
complicated.
agree.
Sets.
So, Azadeh, I understand, but the thing is that this is not the only way to do the proof. By introducing this capability, this way of doing things in Civil, remember, I did not take away anything else. If you like,
I think I can do this proof without sets at all,
great,
but.
and Civil will allow you to do that proof too. You see what I mean?
But then you have to introduce all these contour.
No.
business.
I mean, I would probably use commutativity and maybe.
Yeah, why not?
And then.
Civil will allow you to do it. Why not? So, I mean, it's not like I am in love with this shit, okay? So. That's why I'm saying it's extremely important. When I add all these bells and whistles that you don't take any other proofs out. So the set of proofs that are possible to express in Civil continues to grow. You never take anything out. It's a matter of preference. Some people like this way, some people like that way. Some people's mind change. Like 10 years ago. You won't touch commutativity with a 10-inch pencil as opposed to a long code. But now you are in love with it, people's mind change.
Really that.
So what I'm saying is that it's a matter of your level of comfort also, you see,
No,
with something.
This is not about like preference of one method over the other.
Yeah.
But I mean, I think the same, I'm kind of trying to make the same observation that if the code looks so simple and the proof looks so complicated,
Yeah.
something must have gone wrong somewhere, no?
Now you are
No,
looking
I
like
think so.
Andre and children, no?
I think it's fair to say that, if you really want correctness proofs, you have to be prepared to accept that you must enter forms of statements and understanding into the system that you would not have to enter if you were just interested in writing code.
Yes, I agree with
There's
that.
no way of getting rid of
Yes,
some distance.
yes, yes.
I think that what you said before went a long way to placate me, because
Yeah.
the moment I see that there's a methodology behind what you did here, okay, in terms of frames and permission logics and so on, I think that makes it
Yeah.
easier to accept.
Yeah.
The distance becomes easier to accept because there's a methodology behind it.
Yeah, you just expressed an appreciation for a principle that is very, deeply embedded as I mean. It's known as the principle of least innovation. I was taught this principle by my good friend Anna, whom you also know, recently received an award. Right, so try to minimize innovation. That's what I do, that's how I was able to convince you. If I had invented permissions at the same time as I had this inventing all this other nonsense over here, you would have not able to survive.
Absolutely.
Okay, so any further questions about this example? No? Okay, how much time do we have left?
Half an hour.
Wow. I mean, should we, what do you do? I mean, there's no way we're going to cover all of this. What do you think we should cover in the rest 30 minutes that I have? So I have this inductive sequentialization business. Then I have the relation to blah, 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 other things that go on in the research community, right? And then we have the larger case studies.
Maybe we should do the relation largest case studies and then if we have time.
Okay, all right. We're going to skip some stuff, okay? All right. So, so the idea, so the part that I skipped, let me just say a couple of sentences about it. It has to do with the treatment asynchronous in Civil. And why do we set aside asynchronous programs as separate from ordinary concurrent programs? It's because of the nature of techniques that are employed in Civil, which essentially have to do with summarization of code. And in asynchronous programs, you often find the need to summarize code that is in kind of different threads or different processes, so to speak. So that's why we need some method to be able to synchronize or summarize asynchronous call chains. That was what all that stuff that I skipped over was talking about. That was, for example, what got used in doing a fairly compact proof in terms of the invariant complexity of the Paxos protocol, for example. All right, but that was like a little subsection that I just carved out. So now we are moving to the end, towards the end of the tutorial, where we're trying to set the Civil work in relation to all the other threads that are popular that in the research community targeting the same problem. Okay, just try to give an idea of the relationship and the pros and cons, so to speak. Okay, so this is my view of what is the good thing about Civil. So the good thing about Civil, I think, is that it is literally, it's using very, very simple things. So what are the ingredients here? The ingredients are invariants, right? Then you have commutativity, right? And you have this kind of program rewriting, systematic program rewriting, which is enabled by doing these kind of simulation proofs where the bulk of the simulation is hidden, right? And these very, very classical things, all these were known, and of course there's linear logic also. By the way, when was linear logic invented or linear type system? Does anybody know?
89, maybe.
89?
Something like that.
Oh wow. So like this is all so classical that this was in existence before I embarked on my research career. And this is a fact that I derive a lot of confidence from. Okay. What we are doing over here is that we are simply orchestrating these very, very simple things in a style, which owes its genesis not to philosophy, but to just try and attempts to do proofs and seeing, by virtue of examining programs from lots of different sources, what works and what does not work. That's all. So that's the good thing, right? In my opinion. There could be downsides too. And in all fairness, I should admit all the downsides there are. The biggest one would be that, because at the end of the day, this is a somewhat heuristic approach. It could be a potentially never-ending stream of these kinds of rewriting tactics that we have. And that's a danger. That is a danger. Another thing is that the whole thing is much more sophisticated, right? Because now you have to orchestrate these different things. So if your primary goal is in automation, then you have created a new problem for yourself. How do you automate this orchestration? Okay. All right. Now, In contrast to the work on substantial work, I would say, on program logics, where do they get their power from? They derive their power from having, custom reasoning rules inspired by challenge problems also, right? And unlike this work here, which is very classical, this is all, like bleeding edge stuff. Like every month, there is a new program logic, right? It's a lot of innovation here. So it completely violates the principle of least innovation, right? So this is good because you can build very, very custom reasoning engines or rules that can, for those examples that they were that inspired them, can seem to give you very ergonomic proofs, right? But it creates problems. One problem is something that we've already seen, there's like a new program logic every month, right? The second problem is that because these rules start getting borrowed, it's difficult to use generic solvers to address the automation needs of these borrowed rules. Okay, so I would say that, these are the things that I can see that work for and against each of these techniques. What these methods are doing is they are pushing a lot of complexity into the logic, so to speak, for which erasure is very simple, right? You just drop all the specifications and you get the code. Whereas we are getting our power that replaces all that complicated logic by doing everything using programs, and using programs as abstraction of program, and programming abstraction of program, right? So everything is very sort of like operationally imperative in that sense. Okay, good. So that's that. Now, this one's very interesting. So you saw about these layers, right? So some people, who have worked on modules before, they might wonder what is the connection between these layers and modules. Can you think of these layers and modules or not? And the answer is no, you cannot. They're very different from each other. So each layer in a Civil program is a whole program by itself. Okay? And so the semantics that you need to state the meta theorem for soundness of Civil, it needs semantics only for a whole program. Now, if you look at formal module systems that are investigated in the PO community, they are trying to compose program pieces, right? And as a result, they need semantics for those program pieces also. So they need semantics for partial programs, which is much more complicated and dicey proposition. So in a way, the meta theory there gets much more complicated for those kind of formal module systems. Okay, so now I wanted to spend some time talking about two large programs that were developed with Civil. We're not going to have time to cover both, I think. So let me tell you about these two. So one of them is Paxos. Paxos is, the challenge is that it's a message passing system. And there is not any fine-grained shared memory concurrency there. All the complexity there is in the interleaving of these message handlers. So there's that one thing. And then on the other side, we have a concurrent garbage collector. So here, there's a lot of fine-grained shared memory reasoning going on because the mutators, there could be arbitrary number of mutators that are running concurrently with a collector. It's not a stop the world garbage collector. So the mutators could be running at the same time the garbage collection is happening. And there are many different layers with many different kinds of synchronization problems being solved there. Which one would you like to hear about? Paxos? Okay, let's do Paxos. Okay. Okay, so Paxos is a solution to the consensus problem. So what is that? So you have a collection of distributed nodes, and each node can go down at any point in time, arbitrary number of nodes. And when it goes down, it stays down. Can't do anything after that, okay? These nodes are communicating amongst each other. And the goal is for all of them to eventually reach consensus on a value. So everybody says 3, right? Or I don't know yet. You can't have a situation where one guy says 3, the other guy says 5. Right. Okay. Now, the messages that they are sending to each other, they could be delayed. They could be even infinitely delayed. Okay. All right, so that's the setup. The way this is solved by this very well-known method called Paxos is that values can be proposed by any one of these nodes. The only protocol that they have to follow is that each proposal must be with respect to a round number, which you can think of as an integer. And they must guarantee that they use rounds in a linear fashion. So 2 different nodes should use disjoint rounds. And if a node chooses to move on from a round because it's not getting back, it should use a new round number. Okay. So that's one requirement, and the other requirement is that these rounds are totally ordered. The round numbers are totally ordered. These facts are somehow used in the arguing the correctness. So the protocol guarantees that. So what happens is that there's this back and forth chit chat going on between these nodes, and it could happen that within a round, consensus is apparently reached, and these nodes agree, right? They never go back. That's the property. So this protocol guarantees that if 2 rounds are in R prime, they both reach consensus, then the values that they agree on must be the same. Okay. All right. So now I'll give you a little bit more detail about what the implementation looks like. Okay. So we have these 2 types, node and round. So node is the type of the IDs of these distributed nodes. Round is this round by round consensus that I was talking about. Okay. And then in the implementation, which is at the lowest level, right? What you have is are these proposers. So in a real implementation, the proposers would be one of the nodes, but here I'm separating those 2 roles. So I'm thinking about these proposers as separate processes. And this should be P0, P1, P2, and these are A0. And then there are these acceptors. So these are the nodes. So what the goal is for these acceptors to reach consensus on a value. And these proposers, which could be an arbitrary number of them, 1 for each round, they're proposing values to them. Okay. So if you look at the state, these acceptors, they are stateful, and each node has some acceptor state. So it's a reactive system. A message comes in, the message creates some update on the state, and then the next message comes in, it updates the state, and so on. The acceptors are kind of stateless. Their only state is in the channels over here. So there's a channel for each round, and the contents of that channel. So each one of these nodes, each proposer is a separate process for each round. And these channels contain responses for the messages that were sent from the proposers to the acceptors. Right? So it's we are modeling these channels as multisets of a particular response type. Okay. And we have just decided to separate answers to 2 different kinds of messages, to join messages and to vote messages into different channels. Okay. So far, so good. Any questions about this? Okay. This is our top level specification. We want to prove that the system implements an atomic action in which consensus is reached in 1 step. Magically. Okay. So this is that atomic action, A underscore Paxos prime. There is a decision variable in which the decisions for the various rounds are stashed. And here you can see that it's option also, optional value, because you may not have reached a decision. and look at the code for this step. Was it ignore these this assertion about these linear permissions? Ignore that for a second. It's saying that if my decision is initialized to none for all rounds, then at some point, decision is havoked while satisfying the state. The state constraint says that for all rounds R1 and R2, if decision R1 is sum and decision R2 is sum, then the two must be the same. Magically. So this is very interesting because in this interface, you have the property that any one execution of this atomic action gives you the desired property that I was talking about earlier. You also have this information that this action cannot be executed more than once. Why is that? It's because of this linearity business. Because I'm also stating this assertion that I have all the rounds supplied as input here. These rounds are needed in order to execute this because that's a parameter. And all those rounds are getting consumed here. This means that it is not possible for the client to call this more than once. So those two facts together, the specification of this atomic action and the fact that this can be called at most once, gives you this property that I was talking about, that magically consensus is reached in one step. Yes?
Looking at the first assertion, it's not clear to me what the type of RS is.
Oh, it's a set of rounds.
Okay, so
It's a set of all rounds.
The assertion says it contains all rounds.
All rounds, yes. Yes.
Two questions.
Okay.
So program that wants to call that, how does it get all rounds? And then the second one would be if RS is linear, then the body would violate that linearity.
Why is that?
Because R is not used anywhere in the code.
Oh, yeah. That's because our notion of RF of linearity is, there's a strict one and the weaker one, affine. I think this is the affine. What we use is the affine. You can drop into the code, just handle it.
Okay.
Yeah. Now, for your first question, where does this thing get it from? I mean, that's just a precondition. The client can get it, right? Because they're a set of all integers, right? But you can get it only once in call. Yeah, that's all. By the way, there is some missing functionality here in case you may have noticed. Why you might be wondering, why do I have only this atomic action as the spec? Ideally, I should provide an API for examining the value that a particular node has reached consensus on. There might be some client working on each node that wants to look at what that value is. So I should provide an accessor function with the node as an argument also. And yes, by the time we got done with this, people lost interest, I lost interest, we did this. That API, I think, is a very important API, and I would like to add it. It's a work in progress. I'll do it. And then it will be complete. Because the idea is that this particular API for reaching consensus is called by somebody. But after that, the result of reaching consensus can be obtained by calling this other API on any node. Okay. Okay, so now I'm going to explain to you the refinement proof, going top down. So I showed you the spec. So at the next level, what ends up happening is that instead of one action, you have multiple atomic actions. Okay, so instead of that A paxos prime, which you saw there, we have these other actions, A paxos and A start round, and A join, and A propose, and A vote, and A conclude. Okay, and the connection between A paxos and A paxos prime is that A paxos refines A paxos prime. Using this machinery that I elided and I did not have time to present, called inductive sequentialization. Basically, what's happening is that these atomic actions can be invoked from each other. So for example, this atomic action A paxos, it creates A start round. A start round creates A join and A propose. And these modify some global variables and so on and so forth. So, but by calling APAC source, a whole sequence of asynchronously called atomic actions is launched. And we have to prove in the step that that entire thing, no matter how those interleave, those atomic handlers execute, they behave like that glorious spec that I showed you on the last slide of a single atomic action. And of course, you have, in addition to the decision variable, you have some concrete, some more variables here that are getting modified here. But these variables are not yet the variables that I showed you at the very beginning, which were the implementation variables. These are intermediate variables. Because there is one more step. In the next step, decision is gone, is hidden. The other variables that I showed you on the last slide, they're also gone. And 3 new variables are introduced. These are the same variables that I showed you when I was showing you that pretty picture with the proposers and the acceptors. And here, now you have actual running code procedures. So you have a procedure paxos that defines a paxos. You have start round that defines a start round. And these things, they have loops in them, and they're making asynchronous calls, and then they are sending messages to channel, and blah, 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 blah. So it's pretty nice. Okay. So that's the story.
Here's one question. The last thing you had async atomic. What is async atomic?
Okay. Go back.
I think these putting seem like the whole problem.
So why do I have this async keyword?
Yeah.
So notice that some of these atomic actions can be created by other atomic actions. So this is just a typing thing. If you want an atomic action to be created by another, to be creatable, asynchronously creatable, you have to declare it as an async action.
I would say that an atomic action creates another atomic action. Does that exist within the lifetime of the first one, or completely?
So this is not the pending async.
So this
It means that it has been launched
okay.
as a side effect of executing that action, and it will execute at some time in the future. Yeah. So this, I did not have a chance to explain earlier, right? This is another way of modeling communication between processes. So oftentimes, communication among processes is modeled by explicitly putting buffer messages into buffers, like queues and so on, right? But if you don't have any ordering constraints in how these messages get executed, you can model them as just asynchronous calls. And oftentimes, then what happens is that these asynchronous calls are generated by a procedure that you want to make atomic. So when you make them atomic, then you have as a side effect of the atomic action, launching these pending async calls. Now what? Any questions I can answer? Yeah.
So I have a question on the other problem that you described, that is concurrent garbage collector.
Yeah.
So when you prove the correctness of the concurrent garbage collector, usually what we want to use it with another program.
Yes.
Where we just call the garbage collector and it should work as is.
Yes.
So in that case, the proof that you have done for the collector,
Yes.
can it be also integrated or composed with the proof of the original program?
Yes.
Can we
Yes, the answer is yes. Yes. What will happen is that, why don't I show you the spec? No, it's further up. So the situation that you are describing is something like this. This is the API that the client program will call. You want to be able to allocate, you want to be able to write a field, you want to be able to read a field, and you want to be able to do some operations inside roots, for example, right? And when you are doing this, you want to pretend that you never reuse an object. It's like an infinite family of objects that each object is allocated only at most once, right? So precisely that is the illusion that is provided to you by the concurrent garbage collector. So in the API, you have these things. The garbage collector is sort of like running on the side. And at this abstraction level, the garbage collector disappears. You see, it must disappear because at this level, it has nothing to do, because we are already at the level of this infinite collection of objects. But when you try to refine this to lower levels, the garbage collector comes into existence and things like that happen. Yeah.
So with the, we can separately prove for the some properties of the garbage collector, I can replace one garbage collector with the another, and still the program should work correctly.
If you have shown that the garbage, let's call them A and B, garbage collectors. A refines the exact same atomic action spec interface as B, then indeed it should be possible to stitch out the proof of one with the other. There is, to give you full disclosure, there is no mechanism for it. Basically, you write your layered program in such a way that what you have to do is you have to write out the proof of garbage collector A in this file, garbage collector B in this file, and then your client program in another file. And if it so happens that the atomic actions used by garbage collector A are the same as the one used by B, then it should be the case that if you verify your client together with A, or you get the same answer as client verified with B. It's because the verification of the garbage collector code, you're really not using any aspects of the client code other than the preconditions and so on and so forth. Yeah, other than the interface. Yeah, so it should work out. Now, yeah, so but let me tell you, I mean, having said all that, still there is no module system anywhere here. This is still like a full program property, and yeah, okay, all right. Okay. So, Azadeh and then, okay, you go.
So I have one last question, then a request. So the question is, I did not get an intuition on how many layers. So when am I done with specifying layers?
Oh, I have a very short answer to that.
But that's good.
It's when you get tired. That's half.
Okay. So that brings me to my request. Since you're a research engineer at Meta, you probably know that recently, last year, there was a paper out where they described how they did the formal verification of their IPC of their microchannel in Iris. And they were pretty happy with that. Can you please do the same thing and compare that to that, such that I can understand
The difference.
the difference?
Yes. So you want to see
I know
that
the difference, but I don't know the order of magnitude with that.
you want to see the same program verified using Iris and verified using
It has been verified with Iris, so you don't have to do that.
Yeah.
You only have to do that with Civl.
Yeah.
I'd like to understand like.
This is a totally reasonable request, and Constantin, take notes. Report back in 1 week, okay?
So this business of the permissions, I think you acknowledged a little bit, but at least some of it is about taking the global invariant
Yes.
and trying to model it. What if the global invariant that you need is not a state type of invariant? For example, for some sort of locking protocol, what if I wanted to say that globally everyone who acquires a lock will eventually release it because I need this to kind of put,
Like this.
one step non-blocking.
Yeah, so that one. So you're saying that the assumption, the global fact that you want to inject is not a safety property. It has a liveness component to it. How do you do that?
I think the liveness is a little too far. I'm just saying that basically I'm interested in an invariant. That is not a state invariant. What if it's a transition invariant? What if it's, it's a behavioral invariant rather than.
Okay, can you give me an example of that? Just so I can get a little bit more.
That globally every lock is eventually followed by another.
Oh, I see. Globally, every lock is followed by an unlock. And, okay, I get that.
So I did not even proving liveness, but I just need this.
Good. But I understand that, that particular fact, but let me tell you, how would you use this? What's a typical way in which you use this to get your desired effect? Can you just say a little bit about that?
I have to invent property and, whole example around this, but you understand that, this is kind of like a basic locking protocol kind of thing, right? If everyone can willy-nilly acquire a lock and not release it, you're all dead.
So, but I think the reason I wanted to know that is because that particular thing is very easy to encode. In fact, Constantin showed how to encode it in the early part before the break. So what you do is to encode that one, you introduce a global variable lock.
But this goes against, this is kind of like introducing ghosts, right?
Yeah.
So, but my question fundamentally is, how do I know where I stand? You say that, instead of really introducing ghost variables, we do this permission thing. No, whatever.
No, I didn't say that. You remember, again, you never take any flexibility away.
No, I'm not.
But because it's not an opinion that we should use permission. If something without permission is doing the job, then I think it's better to use that. Why get into all this mess?
But Constantin was saying that the alternative to that is we introduce this kind of ghost
that
variables,
particular
exposed
case.
program locations.
Yeah, in that particular case.
In that particular case, so that was an alternative, right?
Yeah.
But permissions are in some sense the better alternative.
They're more succinct, writing,
Exactly.
producing all these control locations.
So I think
In the case that you are talking about, I'm not seeing any advantage to permissions. Because if you just have a global variable that records which thread holds the lock, and you put an assertion inside the base saying that the global variable is me, right? You will of course also need a notion of me or a thread ID. I think that's good enough to capture what you want. Now, as far as so that's why I was probing a little bit more on what you are going to do with this information, because maybe then I will know that it is not enough. But just to encode this fact, just a global variable.
I specifically asked this question because of this comment that you made about in Civil we try to model a lot of things with code.
Yeah.
So this sort of, it kind of feels like an abstract piece of code that, the
Yeah.
lock followed by unlock, ignore everything else.
Yeah.
But maybe I missed it, but you haven't showed anything like this, that, certain global property.
No, so you can do that, right? So for example, let's say that you have a large program and it has this lock followed by an unlock in one place, and that is being used to establish some other crazy thing somewhere, right? The first thing I would do is that I would eliminate the lock implementation and abstract to this very simple thing. Now I have another program in which I have these conceptual locks, which are getting acquired and released in this very nice way. And I have the rest of the program already there. And I will just do something very over there. We're using that abstract lock. Yeah. It's great. Exactly. For the doctor. Yeah. You had a question?
Yeah, there were 4 questions about the situation where you have to give some obligations of unlock all the law. So for example, if you have a problem determination, which depends on the fact it's always unlock, how in general do you approach this?
So is that same question that you asked? So then the same answer should work.
I had a specific representation question. This question is.
So your question is.
But you don't prove liveness, yes, right?
Yeah, so we don't know how to do liveness. We don't know how to do liveness. Yeah. But if you have a safety property, right, that depending on this property that locks and unlocks are happening in automation, then this is what I would do. If the lock implementation is complicated, I would just like abstract it to this conceptual log thing. Now I have a program with conceptual logs, and I'll do whatever safety proof I want to do based on that. It's very natural.
So you produce those right, it's some extra position of your policy.
You don't even have to do that because, you know, just to encode this property that I acquire only those logs that I own. I just need to record, introduce the notion of a thread ID, and I need to record which thread goes a log into the here. I suppose you can do something like what you're saying, you know, sequences and so on. But I don't know if that thing is going to help you any more than this other encoding with the global here. Wrap up. Okay, so we should wrap up. So we have, you know, one little nugget here. Open problems. So I just thought I should mention that all of this, you know, is good, you know, but there's a lot of problems. To build any kind of verifier and to do practical proofs, ignoring all those refinement machinery, because at the end of the day, you are doing something that boils down to solving verification conditions, also known as deductive verification. There are problems there, right? So one problem is that you want your proofs to be predictable and reliable. Meaning that if I have not changed anything, if I just rerun a verified proof on a different machine, it should not start failing. Now, because of the heuristic that I involved in deductive verification inside these solvers, oftentimes things are predictable. And it's something that we have to address. There is no magic here. Through a combination of improvements in the solver technology and improvements in the methodology according to which we use those solvers, this has to be brought under control. Otherwise, you know, we'll just keep writing papers, and you know, none of this will ever be used for building real systems. Another problem is the debugging failed proofs, right? So you are trying to figure out some way in which you are going to split your invariants and, you know, proof into multiple layers, and then you have invariants that you are going to propagate. You know, something is not working. How do you make progress? I don't know. These are hard problems. This other thing that actually is a good thing to point out, because it receives a lot of attention from the automatic verification. The way I explain this emphasis on automatic verification is that so Civl is a proof checker, right? Just like we have a separation between a type checker and a type inference. Similarly, you have a separation between a proof checker and a proof inference algorithm. So Civl is basically a proof checker with a whole bunch of automation built in. But at the end of the day, the proof outline has to be supplied to you, has to be supplied to the tool. And some of it is actually quite tedious, to be honest with you. Especially the most tedious part for me is the part that is just propagating simple things up and down call chains, right? The more sort of, how should I say, intellectually appealing part, which is trying to come up with the appropriate arguments and how to split the system into pieces. Those parts I actually enjoy, and I think any programmer will enjoy. Programmer will enjoy very cool. So there's something to be said here, right? The issue is that, you know, the technologies that we have today for automatic verification, they tend to be all or nothing. You have to do everything automatic or you don't get nothing. So what is the right way to harness all that amazing technology towards making something like this system more usable is an open question. Reasoning about shared and mutable data structures, this goes back to all the framing discussion that we had, in a way that doesn't, what is the phrase I'm looking for here? Pulling the baby out of the hot water? Would that be appropriate? Yeah, so like I was, in response to a question Jakob asked earlier, yes, framing is important, but so are 1 million other things. So in solving framing, if you just sacrifice a huge amount in other things, I don't know if that's a good trade-off. So to me, this is an open question despite the Bazilian papers on separation logic. Then problems specific to Civil. So we use commutativity checking quite a bit, right? At the end of the day, it boils down to solving verification conditions. Everything boils down to verification conditions. Now, if your atomic actions are not deterministic, right? They are uninitialized variables. It's very common. Then these verification conditions in general would have quantifiers in them. And but maybe they are not completely arbitrary quantifiers, and maybe you can do specialized quantifier relation. We have done a bunch of work in Civil, but this we can certainly use more work here. Layer inference, right? So all these layers have to be annotated explicitly. But the layer annotations at various places in the code, they bear a strong connection to each other, and maybe all those layers can be like automatically inferred here, right? So I just write code, and based on the call chain and the way I'm using variables, the layers are just there, right? And things like that. Modules are also important because sometimes I really want to be able to split the verification of a large system into pieces of Civil code that could be checked independently. And when I put them together, I don't have to recheck the whole code all over again. A lightweight module system like this, like what happens with commercial programming languages, not the fancy semantic modules, would be very helpful, I think, for developing large systems.
So there's one thing that I had expected to see in this slide.
Yes.
That we maybe have that a bit there, but I didn't understand that. It's the problem of, let's say, layer synchronization and layer drift. I have multiple layers. Now I don't just have one program. Down at the bottom, I have my implementation. There's a lot of stuff. Then I have these layers on top. Now I change the program. I also have to corresponding maybe make change the layers. Yeah. And this is kind of a classical software engineering kind of how you have multiple things.
I mean, it is there. It's part of software engineering. Basically, it's like proof engineering, right? So the analogous problem with classical verification methods is you change the program. Now you have just a massive, large inductive invariant. Now you have to change the invariant. Here you don't have one large invariant. You have this split into pieces. But still, if you change something here, it's going to have blast radius. Now, one would hope that if you have separated into different layers as separate concerns, then if you make, so for example, in the example that Constantin had, remember he was making the point about the ticket allocation being separated out in a layer from how you use the ticket allocator. So if you made a change only in the ticket allocator, then maybe the blast radius would not go past beyond that the layer. Yeah.
Do you sometimes have proofs that kind of look like this, that you have the implementation at the bottom, then you have one abstraction layer here, have another abstraction layer here, and then there's at least up-bound abstraction, which corresponds to the ultimate property that you want to prove. So that you may use multiple abstraction layers to prove the property ultimately.
Not so far, but I can easily imagine that could happen too.
I mean, in the garbage collector, when you have, for instance, this stat that you put this root or whatever into one set and it's implemented as a stat, this is sort of different from everything else that happens.
Yeah, but what I don't know is whether, today our layers are totally ordered. So there's not even a way to express a partial ordered set of layers. So today we are forced to do things in a particular order. Now I don't know whether in some situation, the proof that we have done, it can actually be relaxed. That's why I'm going to say yes.
This might correspond to splitting up the proof into
a different one. Yes, I agree with that.
Nothing to do with each other.
Yeah, exactly. Absolutely. Yeah. Yeah, I mean, clearly, right? I mean, the thing is that if you are using in one part of your program, fiber stack, another part of your program, you know, sometimes current queue, right? They are completely isolated from each other, right? So, yeah, I agree with that. And I think that your thinking is correct. It should happen, yes. Yeah. We're done. Now, in praise of the presenters, I have to say that this is one event where we steadily gain attendees as opposed to steadily losing attendees. But that may very well have been due to the small number of attendees to begin with. So I don't know if we can truly generalize here, right? All right, thank you guys for your attention.